Hi everyone, welcome to PrepFusion. So we are going to start our new subject now, that is electronic devices and circuits. So communication system and EDC will run parallelly. So as of now we are going to study EDC, right? So in EDC mostly 4 chapters are there: basic semiconductor physics, PN junction and diodes, then BJTs, and then MOSFET and MOSFET. Okay, and miscellaneous, here all the concept will be there from all 4 chapters. So mostly there are 4 chapters. Now this is the most important one, basic semiconductor physics. Okay, basic semiconductor physics, 50% of the questions will be framed from this particular chapter only. And if you don't study basic semiconductor physics, that means you are not going to understand any of these chapters. So if I want to put the star, I will put 4 stars on this one. After that, importance comes from here. I will put 3 star on this one, MOSFET and MOSFET. Okay, and then I would put 2 star on PN junction and diode and 1 star on BGTs. Okay, and in the miscellaneous, all the concept will be there from all the chapters, right? So this would be the flow. So first we are going to study basic semiconductor physics, then PN junction and diode, then BGTs, and then MOSFET and MOSFET. But basic semiconductor physics is very, very important. Now, one important thing, before starting EDC, you need to have patience. Here it will not happen that, sir, within 10 minutes, sir, I will be able to solve the questions. Some numerical problem will be there, sir, I will be able to solve it. No. This subject requires the patience. You need to have the patience. First, we will understand the theory, then we will move to the formula, and then we will move to the questions. Because here, if you don't understand theory, then formula will be of no use. If you want to utilize the formula, that means you need to study the theory in a good manner. So you need to have patience. In the beginning, you may feel like that, sir, what is going on? How we will be able to solve numerical problem out of it? But you will be able to solve numerical problem. You need to have some patience. So this particular lecture, this is going to be our first lecture. This will be completely based on theory. There will be no formula, nothing. Here I will be explaining you the meaning of semiconductor, why we are studying semiconductor, and how we are getting conductivity out of semiconductor. Okay, so that explanation I am going to give you. From the next lecture onwards, questions will start coming. But as of now, in this lecture, only theory will be there. Okay, only theoretical part will be there. So let's get started. So what we are going to study, basic semiconductor physics. So all the devices that you see in front of you, you might be watching this video in laptop or in computer or anywhere you are watching this video. You might be watching it in mobile. You are having your earphones. Whatever the devices you are having, in all the devices there are some tiny devices, and those tiny devices are known as semiconductors. So your world, your whole things are running because of semiconductor. If there is no semiconductor, that means there is no world. Okay, so that's why we need to study basic semiconductor physics. So first we need to study about semiconductors, right? Now there are basically 3 kind of materials: conductor, semiconductors, and insulator. Conductor, semiconductors, and insulator, based on the conductivity. What is the meaning of conductivity? Conductivity means ability of driving the current. Let's just say there is some device and I connect a voltage source around it. Now will this conduct some current? Voltage source has the ability of conducting the current. This wire will have the ability of conducting the current, but will this device conduct the current or not? So based on that, there are 3 kind of materials: conductor, semiconductors, and insulator. So if it is conducting, that means it is having high conductivity. If it is conducting the current, that means if it is letting this current pass, then it is having high conductivity. Okay, so for the conductors, conductivity is high. That means in the conductors you can drive the current. If this material is conductor, then it will let the current flow. So from the battery, current will go out, and in the battery only the current will go in, and in the device as well the current will flow. If it is an insulator, then it will not allow the current. Look, let's just say this is a wire, this is my this wire I am having, this is the charger I am having, right? So if I connect this charger and from here if I connect my mobile, then mobile will be getting charged because the current is flowing inside it. But here there is coating, like, right? There is plastic coating here. On the wire there is plastic coating. Even if I connect it and if I hold the wire, will I get any current? Will I get any shock? No, I will not get any electric shock. Why is that so? Because this plastic coating is insulator, right? But the wire that is inside it, that is conductor. So for the insulator means it will not allow the current to flow. It will not conduct the current. If it is not allowing the current to flow, that means it is an insulator. If it is allowing the current to flow, that means it is conductor. So for the conductor, conductivity is high. For the insulator, conductivity is low. What is the example of conductor? That is copper. What is the example of insulator? That is plastic coating on this wire. And if you see, other examples are also there. Wood is also example of conductor, right? Wood will never allow the current to flow, right? Let's just say you take a piece of wood and then you connect a battery around it, and will you be getting some current? No, you will not get any current. You take a piece of wood and then connect a battery around it, will you get any current? No, you will not get any current, because wood will not allow the current to flow. So this is known as conductor and insulator. Now there is something called semiconductors. So in the semiconductors you can control that conductivity. This is the best thing. What I am saying, semiconductors, conductivity of the semiconductors is controllable. That means you can move from here to here. That means you can make the conductivity high as well, and you can make the conductivity zero as well. Basically, the semiconductor can work as a conductor as well, and it can work as an insulator as well. Along with that, you can control its conductivity. What does that mean? That means if I want a very high current, that also I can do. If I want low current, that also I can do. If I want zero current, that also I can do. And as an engineer, you want to be controllable. Controllable for your partner? No. Controllable for the devices that you are using. Okay. You want to be controllable. That means you want the control in your hand. If I give a supply, if I give a particular supply, or if I do any activity, based on that activity, I want to control the things that is happening on my chip. Right? If I have a remote, if I press the button to 25, that means the AC should be working at 25 degrees Celsius. If I press the button at 23, that means AC should be working at 23 degrees Celsius temperature. So as an engineer, I want to be controllable, and semiconductor is doing that particular thing. That if you want to make it as an insulator, you can make it as an insulator as well. If you want to make it as a conductor, you can make it as a conductor as well. Examples are silicon, germanium. A lot of examples are there. Silicon, germanium, GaAs, gallium arsenide. Okay. Indium phosphide, INP. A lot of examples are there. We will study about them. Is that clear? Is this slide clear to you? So every tiny devices that you are seeing, every device that you are seeing, in those devices, some tiny devices are there. Those devices are known as semiconductors. Semiconductors have controllable conductivity. Insulators will have zero conductivity or very low conductivity, while the conductors will have very high conductivity. Examples are there. Okay. So why we are studying semiconductors? Because semiconductors are special. We can control when and how much they conduct, and this controllability will make other devices like diodes, transistors, solar cell, microchips and all. So we will study about all these devices, like what is diode, what is transistor. So everything we will study. In BJTs and MOSFETs we will study about transistors, and in the PN junction we will study about diodes. Okay. So that's why we are going to study semiconductors. Now before studying the semiconductors, we need to start right from the scratch. What do you mean by right from the scratch? So how a particular material is made, how we are made, how everything is made in this universe. So that kind of physics, from that kind of scratch we need to start, that how a particular semiconductor device was made. So in this video, in the first half, we will be just building a particular semiconductor. So how it started? So every single thing, let's just say this is some material. So this material is made of some atoms. So in this material there will be a lot of atoms. So this material is made of all the atoms. Now this atom is made of three particles. In the atom there will be three particles, and those particles are electron, proton and neutron. So every material is made of atom, and atom is made of electron, proton and neutron. So in each material there will be a lot of atoms, and in each atom there will be three kind of particle: electron, proton and neutron. Okay. And this proton and neutron combined is known as nucleus. Okay. So I will tell you the structure of atom, but before that let's study about electron, proton and neutron. So what is electron? Electron is a negatively charged particle having a charge of minus 1.6 into 10 to the power minus 19. So it is shown by E. The charge of electron is shown by E. Charge of electron is shown by E, which is given as minus 1.6 into 10 to the power minus 19 coulomb. Okay. Mass, very small mass is there, 9.1 into 10 to the power minus 31 kg. Okay. And position, what is the position, that I will tell. So forget about this point, this position I will tell you. What about the proton? Positively charged particle. It is having the same charge. This was a negative charge, this is just a positive charge. So here the charge is 1.6 into 10 to the power minus 19. Okay, and what is the mass? Mass is, this is heavier than the electron, right? 10 to the power minus 31. That means after 0 point, after that there are 31 zeros. That means 10 to the power minus 31 is lesser than 10 to the power minus 27, right? So this is much heavier than the electron. And neutron is having no charge, but the mass of neutron is same as the proton. And about the position I will tell you now. So these are very simple things that you have already studied in the chemistry, right? In chemistry you have already studied these kind of things, just I am making you revise. Okay, so now how your atom will look like. So in an atom there will be something called nucleus. Now in this nucleus proton and neutron will be there. So proton are positively charged, neutron are neutral, right? Neutron means neutral, there is no charge. So on the neutron there is no charge, in proton there is positive charge. So positive charge plus 0 charge, what that would be? Effectively it will be positive charge only, no? So in the nucleus, at the center there will be nucleus, in the nucleus there will be proton and neutron. Nucleus I will be showing by the positive sign. Why I am showing by the positive sign? Because there is proton and neutron, proton are positively charged. Now around the nucleus, electrons will be there. Electrons will be walking around the nucleus in a fixed closed path. Electrons will be walking around the nucleus in a fixed closed path. So in an atom there will be proton, neutron and electrons. Proton and neutrons combined are called as nucleus. They will be right in the center. Around the nucleus, electrons will be moving around in fixed circular path. Okay, so let me show you the structure. So this is the structure. So this is a model of an atom. Right in between there is a nucleus. In the nucleus there is proton and neutron. Effectively it will have a positive charge. Effectively it will have a positive charge. Around the nucleus there are electrons. These are the electrons. These are the electrons. Electrons are revolving around the nucleus. Electrons are revolving around the nucleus in a fixed circular path. It's like our solar system only. In our solar system what is there? Sun is there. In the center sun is there. Now around the sun your earth is moving, right? Around the sun your earth is moving. But earth will always move in a fixed circular path. It's not that, sir, this year earth is moving like this and after that it will lose its radius. It will keep on losing its radius and eventually it will fall into sun. Will that happen? No. Earth will always keep on revolving in this circular path only. Similar things will happen with the electrons as well. Electrons will keep on moving on this fixed circular path. Okay, so this is what I have written. This atomic model was given by Bohr, but scientist name is not important for us to understand the semiconductor physics. As of now we are just learning what we have already studied in the chemistry. So what they are saying, electrons move in a fixed circular path around the nucleus. Now each orbit or you can call it energy level. So this is known as energy level. This is your first energy level. This is your n equals to 1. First energy level. This is your first energy level. So I am calling it n equals to 1. So in this first energy level you can see there are 2 electrons. This is your second energy level. I am calling it n equals to 2. And this is your third energy level. I am calling it n equals to 3. So what is written? Each orbit has a fixed energy. That means if you are walking in this particular circle, if your electron is walking in this particular circle, that means electron is having a fixed particular energy. At any point on this particular energy level, the energy will be fixed. Here. Everywhere the energy will be fixed. Okay, it will have the same energy. But 2 different levels will have different energies. This level will have different energy, this level will have different energy, this level will have different energy. Let's just say this level is having E1 energy, this will have E2 energy, this will have E3 energy. Are you able to understand this point? Okay, but in this E1 energy level, all the electrons will have the same energy. That means if I call this electron as electron 1 and this electron as electron 2, so both electron 1 and electron 2 is having energy of E1 only. If I call this as 3, 4, 5 and 6, so all the electrons 3, 4, 5, 6 is having the energy E2. Let's call it alpha, beta gamma. So alpha electron, beta electron and gamma electron, all the electrons are having energy E3. So in a particular energy level, all the electrons will have the same energy. And if electrons are working in this fixed circular path, if this electron is working in this fixed circular path, it will not lose its energy. Let's understand by an analogy. Let's just say there is some particular center and I ask you to walk around this circular path. I ask you to walk around this center in this fixed circular path. So what will happen? You will keep on walking, you will keep on walking, you will keep on walking, you will keep on walking. But slowly what will happen? You will start losing your energy. So what will happen? Your circular path will reduce. Then again and again you will keep on losing the energy. You will again keep on losing the energy. You will lose energy. The circular path will keep on reducing and then you will fall into this center, right? Just imagine here this is the center and you are revolving. So you will lose the energy. If you are losing the energy, what does that mean? That means your circular path will reduce and eventually you will fall down. But what if you are working with the constant energy? You are that kind of human being, you are an alien who is not losing the energy. So electrons are like that only. If electron is working in this fixed path, then it will not lose the energy. What does that mean? It will keep on revolving around the nucleus in this fixed particular path only, and it will not lose the energy. This electron will also not lose the energy. They will just keep on revolving around that. It's like our earth only. What earth does? It will keep on revolving around sun in a fixed particular path only. It will not lose the energy and fall into sun. This thing doesn't happen. So similarly with the electrons, it will keep on revolving around the nucleus. It will not lose the energy and fall into the nucleus. It will not happen. Okay. Now let's just say this electron from here wants to go into this level. This electron is there in the n equals to 1 level. It wants to go into n equals to 2 level. N equals to 2 level electron wants to go into n equals to 3 level electron. So what will happen? It needs to get some energy. The electron needs to absorb some energy. If it gets some energy, then it can make the transition. What I am saying is that, let's just say this was your energy level E1 and this is your energy level E2. One electron is there in energy level E1. Now if this electron wants to go to energy level E2, what will happen is that it needs to take some energy. Now whatever the energy gap is there, let's just say this energy E2 is 1 electron volt and this energy E1 is 0.5 electron volt. So the gap between them is 0.5 electron volt only. Let's take it 0.3. So gap between them will be 0.7 electron volt. So if this electron gets the energy of 0.7 electron volt, then what will happen is that it will make a transition from this energy level to this energy level. So how much energy it will require? It will require delta E energy. How much energy it will require? It will require delta E energy, which is equals to E2 minus E1. So as you go further from the nucleus, like this particular orbit, you can call it orbit or you can call it energy level. So this particular energy level will have the least energy. As you go further from the nucleus, the energy will increase. Sir, why that happens? You will see it. Don't worry about that. As of now, on a crude level only, I am telling that this will have the least energy, then it will have more energy, it will have more energy. In that manner, the energy will keep on increasing. And you can directly see that this electron is near to the nucleus, no? Who is having lesser distance? Who is nearer to the nucleus? This electron or this electron? This particular electron is nearer to the nucleus. That means this nucleus is making more force on this electron. Let's just say there is some Q1 charge and then there is some Q2 charge. This is positively charged, this is negatively charged. So what they will do? They will attract each other, right? They will attract each other. If the distance is small, then the attraction will be large, and if the distance is larger, then the attraction will be lower. So here the distance is low, here the distance is less. If the distance is less, that means it is more attracted towards the nucleus. So it is bound. This electron is bound by this nucleus. but this electron is lesser bound by this nucleus, and this electron is even lesser bound by this nucleus. Are you able to understand this point? So if it is bound, that means it cannot move freely. What is the meaning of energy? If I say I am having the energy, that means I am teaching now. I can do the activity, right? If I have the energy, that means I can get out of my house and I can walk around the park, right? I can walk around the path. I can do anything if I have the energy. And when I will have the energy, if I am not bound, what if my parents says that you need to stay in the home only, that means I am bound by them. But since now if my age is 25, 26, then what they will say, you are not bound. So similarly, this electron is not bound. This electron is not bound by this nucleus. That means it is having more energy. More energy means it can go out. It can go out easily. If I am not bound by parents, that means I can go out very easily. So similarly, this electron is not bound by the nucleus. That means it can go out very easily. So this will have least energy, this will have more energy, this will have even more energy, here more energy, more energy. So if you go further from the nucleus, the energy will keep on increasing. Okay. So if you are in level 1, if you are in energy level 1, if you are in n equals to 1, then your energy is lesser. If you are in level 2, then your energy is more. So if you want to go from E1 to E2, that means you need to absorb some energy. Another analogy I will give you. Have you seen firecracker? Have you seen rocket? Rocket. Firecracker, right? Some firecracker you would have surely seen. So in firecracker, what do? You will fire it up, you will give some light to it, you will give it some energy, you will give it some heat, right? If you give it some heat, what happens? It absorbs this energy and it will go up, right? It will go in the sky, it will go up in the sky. After some time, what will happen? It will fall back. There was a firecracker, there was this firecracker, you gave it some energy, you gave it some heat, you gave it some fire. What happened is that this rocket went up in the sky and then fall back. Similarly here, you need to give some energy to this electron. What will happen is that it will go into the higher level and then again it may fall back. And when it is going up, at that time it will absorb the energy, absorbing the energy. So this have been already written, so I will not tell it. So at that time it will absorbing the energy, and when it falls back, it will release the energy. And how much energy it will release? Whatever the energy it has taken, the same energy it will release. If it has taken delta E energy, then the same energy delta E only it will release. Are you able to understand this point? So if it is jumped to a higher orbit, that means it is absorbing the energy. If it jumps to a lower orbit, that means if it is coming from E2 to E1, that means it will release the energy as light or as heat. It can release the energy as light as well or as heat as well. Is that clear to you? Is the meaning of atom clear to you? In an atom, there will be a nucleus. In nucleus, there will be proton, neutron. So effectively, it will be positively charged. Around the nucleus, electrons will be revolving around in fixed circular path. Each fixed circular path will have a certain fixed energy. In that particular path, if electron is moving, it will have a certain energy. As you go further from the nucleus, as the distance from the nucleus increases, the energy of these energy levels will increase. If you are farther from the nucleus, that means your energy will be more. If you are near to the nucleus, your energy will be less. Why is that so? Because you are bound to the nucleus. Now, if an electron wants to make a transition from lower energy level to higher energy level, then it needs to absorb some energy. It needs to take some energy by any mean, by light, by heat, by any mean. If it gets some energy, then what will happen is that it will make a transition from lower energy level to higher energy level. And if it is coming from higher energy level to lower energy level, then what will happen is that it will release some energy. So this is about the atom. And now all these atoms combined will make some material. So you are also made from atoms only. Small atoms will combine and will make one material. Is that clear to you? All good? All fine? Now let's understand what is the meaning of energy. So what is energy? Let's just say there was some material. In this material there was some Q charge. Now around this material, what do I do is that I connect a battery of V volt. So if this Q charge gets the acceleration of a voltage V, then its energy will be Q into V. What I am saying, if some Q charge gets the voltage difference of V. There was some charge lying there, I gave it some voltage, then it will attain an energy of Q into V. That means now this charge can move. Energy means if you are having energy, that means you can move. If you are having energy, that means you can move. So this Q charge was there. Around this Q charge there was no potential, but just as I applied potential V, it will start moving. So a charge Q getting a potential difference of V, then it will gain an energy of Q into V. Is that clear to you? Now what is the unit of energy? Unit of energy is joule. What do you mean by joule? Joule is simply, what is the unit of charge? I hope you know these kind of basic things. Unit of charge is 1 coulomb and unit of voltage is 1 volt. So coulomb into volt. Okay, 1 joule means coulomb into volt. Now what do you understand by 1 electron volt? So there are two units of energy. One unit is joule, other unit is electron volt. In our EDC we will use this one. In signal system, in network analysis we mostly use joule, but in our EDC we will use electron volt. What is the meaning of this electron volt? So similarly what I explained there, what is the meaning of energy? If this Q charge is getting a voltage V. Now in place of this Q charge, if one electron is getting a voltage V, one electron is getting a voltage V. Now what is the charge on the electron? 1.6 into 10 to the power minus 19 coulomb. So if 1.6 into 10 to the power minus 19 coulomb gets an energy of, gets an potential difference of V volt, or you can say potential difference of 1 volt, because we are telling the definition of 1 electron volt, right? We are telling the definition of 1 electron volt. Here what was the definition of 1 joule? If 1 coulomb charge gets a voltage difference of 1 volt, 1 coulomb charge gets a voltage difference of 1 volt, then what will be the energy? 1 joule. What will be the definition of 1 electron volt? If a 1 electron charge, what is 1 electron charge? 1.6 into 10 to the power minus 19 coulomb. So 1.6 into 10 to the power minus 19 coulomb charge gets a voltage difference of 1 volt. Gets a voltage difference of 1 volt, then its energy would be 1 electron volt. So this is what have been written. 1 electron volt is the energy gained by an electron when it is accelerated through a potential difference of 1 volt. Is that clear to you? So this is the meaning of 1 electron volt. So from here what do you understand? Can I write it down in this manner? 1.6 into 10 to the power minus 19. This will be coulomb, this will be volt. What is coulomb into volt? Joule. So 1 electron volt is equals to 1.6 into 10 to the power minus 19 joule. You don't need to mug it up. Never ever mug it up, because what will happen is that if you mug it up, you will get the confusion. Sir, 1 joule is equals to 1.6 into 10 to the power minus 19 electron volt, or sir, 1 electron volt is equals to 1.6 into 10 to the power minus 19 joule. In longer run, this kind of problem you will face. If you just remember it, if you just try to memorize the formula. So here you are not going to memorize the formula. What you will do? You will simply say, okay, 1 electron volt. That means 1 electron is getting a potential difference of V. That means 1.6 into 10 to the power minus 19 coulomb into volt. Coulomb into volt. What is coulomb into volt? 1 coulomb is getting a potential difference of 1 volt. What does that mean? Okay, it is joule. So 1 electron volt will be equal to 1.6 into 10 to the power minus 19 joule. So don't mug it up. Better than that, you understand it. What is the meaning of 1 electron volt? Okay. So let's solve some question. An electron in a semiconductor is given an energy of 3.2 electron volt. Through what potential difference it must be accelerated from rest to acquire this energy? Did you understand this point? An electron in the semiconductor, let's just say this is the semiconductor you are having. In this semiconductor you are having this electron. This is having an energy of 3.2 electron volt. Electron is having an energy of 3.2 electron volt. What is the formula of energy? Q into V. If your charge Q gets a potential difference of V, then it will have energy E. Energy E is already given. Now what is the charge? Who is getting this much energy? Electron. And what is the charge on electron? E only, into potential difference. into potential difference. So what will be the potential difference? Potential difference is coming out to be 3.2 volt only. So from here, what do you understand? From next time onwards, if the energy of electron is mentioned, let's just say energy of electron is mentioned as alpha electron volt, and I ask you to calculate the potential difference. Can you tell the potential difference? Yes, sir, the potential difference will be alpha volt. So if anywhere electron volt is mentioned, then directly you can tell voltage. If energy is mentioned, you can directly tell the voltage. Because in this whole chapter, in this whole subject, we will just talk about the electrons, and energy will be mentioned in electron volt. So whenever I say from electron volt, you need to find voltage. How will you find it? Just divide by the charge. Here what you are doing, you are dividing by the charge. E and E get cancelled out. So what is the answer you are getting? 3.2 volt. Right? So did you understand the meaning of electron volt? Did you understand why I spent so much time here? Why I spent so much time on electron volt? Because at a lot of places, energy of the electron will be mentioned. Then you should know that what should have been the potential around it. If energy of the electron is alpha electron volt, that means I should have given alpha potential. I should have given alpha potential difference around this electron. Then only it would have got alpha electron volt energy. Is that clear to you? Okay. Next question also very easy. A proton. Proton is accelerated and gain this much of energy. What is the energy? Energy is given as Q into V. Energy given is 4.8 into 10 to the power minus 16 joule this time. So this is the energy of proton. Okay, through what potential difference it must be accelerated. So what is the charge on the proton? Same charge as electron, 1.6 into 10 to the power minus 19 into potential difference. So what will be the answer you will be getting? 3 millivolt, right? Because 3 and then, okay, no, 3 kilovolt. Sorry guys, 3 kilovolt. 3 kilovolt. So that would be the answer. This would be the potential difference. Okay, very simple question. You don't need to convert it to the electron volt, right? Why would you convert it to the electron volt? Directly you can find the answer. Or what some people would have done is that 4.8 into 10 to the power minus 16 joule is there, no? So how will I convert it to electron volt? So I know that 1 electron volt is equals to 1.6 into 10 to the power minus 19 joule. 10 to the power minus 19 joule. That means from here, what would be your 3 electron volt? So 3 electron volt will be equals to 4.6 into 10 to the power minus 19 joule. Right? So answer would have been 3 electron volt. So it is having 3 electron volt energy. So here what could have been given? Yeah, but this is 4.8 into 10 to the power minus 19. Now if I need to do 3000 electron volt. So 3000 electron volts means here I am multiplying with the 10 to the power 3. So here also I will multiply with 10 to the power 3. So what I will be getting? So what does that mean? That means this was given as 3 kilo electron volt. So the energy of the proton was 3 kilo electron volt. So what would have been the potential difference? That would have been 3 kilovolt. So every time you don't need to convert a joule into electron volt, right? If you require converting into electron volt, then you can convert it. And for the conversion as well, I am asking you not to mug up the formula, but to think about it. But all good? All fine? Now let's talk about the energy of an electron in hydrogen atom. So in hydrogen atom, you guys would be knowing that there is only one electron, right? So the energy of that particular electron is given by minus 13.6 divided by n square, and this is given in electron volt. Okay, this is the energy of hydrogen electron that is available in hydrogen atom. Okay, energy of electron in hydrogen atom, this is given by minus 13.6 electron volt divided by n square. N is known as quantum number, but as of now you will say that n is energy level. Okay, n is nothing but a energy level. Now this one electron in the hydrogen atom, this one electron will be lying either in n equals to 1, either it would be lying in n equals to 1, n equals to 1 level, or it could be lying in n equals to 2 level, or it could be lying in n equals to 3 level. The electron could be here, this is your nucleus, right? Electron could be here, or it could be here, or it could be here. It could be anywhere. Ideally, it should lie near to the nucleus, but what if I have given it some energy? Let's just say ideally the electron should be lying in the first orbit. It should be lying in the first energy level near to the nucleus. But what if someone has given it some energy and it has reached to level 2? What if someone has given its energy and it has reached to level 3? Or it might have reached to level 4 as well, right? So this could be the scenario. Now if it is lying in the energy level 1, so what would be its energy? Its energy would have been minus 13.6 divided by 1. What that would be? Minus 13.6 electron volt. If it is lying in the energy level 2, what would have been its energy? Minus 13.6 divided by 2, so 2 square will become 4, this much energy. And if it is lying in the energy level 3, then what would have been its energy? This would be its energy. This has become minus 3.4 electron volt, and this has become minus 1.52 electron volt. Okay. So what I am doing is that with respect to the energy level, with respect to energy levels, I am plotting the energy. So on this axis, I am plotting the electron energy. Sir, how this formula came, you don't need to worry about it. No one will ask you. Okay. I will use this concept to make you understand something else. That's why we are studying it here. Sir, how this formula came, no one is going to ask you. So electron energy on this axis. Okay. Now this is the nucleus, right? This is the nucleus that we are having. This is the nucleus that we are having. So I am taking the nucleus as a reference. This is my nucleus. This is as a reference I am taking. This is my nucleus. This I am taking as a reference. After that, this is my level 1. After that, this is my level 1. This is your n equals to 1. N equals to 1. This is your n equals to 1. N equals to 1. Right? What was the energy? So let's write down n equals to 1 here. What was the energy? Level 1 was there. What was the energy? Minus 13.6 electron volt. Now n equals to 2. N equals to 2. What is the energy? Minus 3.4 electron volt. And then n equals to 3. N equals to 3. What is the energy? Minus 1.52 electron volt. Which number is larger? This number is larger or this number is larger? A lot of people will directly say, blindly they will say, sir, minus 13.6 electron volt is larger. No, it is not larger. There is a negative sign. No. Minus 2 is larger or minus 4 is larger or minus 2 is larger? Minus 2 is larger, no, because there is a negative sign. So this is larger. So as you go upside, as you go upward, the energy of the electron is increasing. As you go upward, the energy of the electron is increasing. So whenever we walk in the upward direction, the energy of the electron will increase, because we have taken nucleus as the reference. Taking the nucleus as a reference, as we go in the upward direction, energy of the electron will increase. And that is certain for all the atoms, not only for hydrogen atom. Here we are talking about hydrogen atom only. First we will take the reference of hydrogen atom. First we will understand everything about the hydrogen atom, and then we will relate it to the semiconductor. So what do you understand? In hydrogen atom there was one electron. That electron could be lying in n equals to 1, n equals to 2 or n equals to 3 energy level. Okay. If it was lying in the energy level n equals to 1, then its energy would have been minus 13.6 electron volt. If it was there in n equals to 2, its energy would have been minus 3.4 electron volt. If it was in n equals to 3, its energy would have been minus 1.52 electron volt. Sir, how this formula came? You don't need to worry about that. So as you go upward in the, as you walk in the upward direction, then the energy of the electron is increasing. Okay. So this point you need to remember. Somewhere when we study our Venn diagrams, I will relate this point. All good, all fine. So this is the theory that has been written here. An isolated hydrogen atom has one proton in its nucleus and one electron. Isolated means it is not being affected by any other atom. Isolated means only one is present. It is not affected by anyone. Okay. This is the meaning of isolated hydrogen atom. So it is not affected by any other parameter. It is not affected by any other atom or anything else. Isolated. It is completely isolated. So an isolated hydrogen atom has one proton in its nucleus and one electron. In Bohr's model, the electron can be only in fixed certain energy level. This we have already discussed, that electron would be either in this energy level or in this energy level or in this energy level. Okay. Given by, the energy is given by minus 13.6 divided by n square electron volt, where n is the energy level number, and these levels are well defined and separated by the gaps where electrons cannot exist. That means electron will be either in n equals to 1, n equals to 2, n equals to 3. It cannot be lying in between. Are you able to understand this point? Either it can lie here or here. It cannot lie in between. That means electron can lie in a particular energy level only. It cannot lie in between. Sir, why we are studying all this? Where it will be used? It will be used somewhere. So have some patience. Okay. You need to have some patience. It will be used somewhere. Let's understand the meaning or difference between energy level and energy state. So let's understand it by an analogy. Let us say there is a one building. In this building there are a lot of floors. Floor 1, floor 2, floor 3. 3 floors are there. So these floors are known as energy level. Now on this floor there could be a lot of rooms as well. Let's just say on this floor there are 3 rooms. On this floor there are 2 rooms. On this floor there is 1 room. So this room is known as energy state. That's it. This is the difference between energy level and energy state. A lot of places I have seen that people will use energy level, energy state continuously. Like they would say energy level and energy state both are the same thing. No. When we study Fermi directed distribution, at that time I will tell you there is huge importance of energy level and energy state. So Fermi direct distribution is defined for energy state, not for energy level. So this was your energy level, n equals to 1, n equals to 2 energy level, n equals to 3 energy level. Now on one energy level, here you could see that on n equals to 1, on one energy level there were 2 electrons, n equals to 2. On this one energy level there were 8 electrons, n equals to 3. On this one energy level there were 8 electrons, right? So on a particular energy level there can be more than 1 electron. N equals to 1, 2 electrons, n equals to 2, 8 electrons, n equals to 3, 8 electrons. So on one particular energy level there can be more than 1 electrons, but on one energy state there can be only 1 electron of the same spin. Forget about this word spin. Somewhere I would have written spin. Forget about this word. This is related to chemistry. You don't need to worry about it. And if you have studied in class 12th, this is known as opposite spin, and this would be the same spin. So of the same spin, we will be considering only the same spin. You don't need to worry the word same spin. You can just ignore it. So what I am saying is that on this particular floor, 2 people can be living. Here also 2 people can live. Here 3 people can live. But in one room only 1 people will live. In one room only 1 person will live. Are you able to understand this point? So on different energy levels, energy level 1, 2, 3. On energy level 1, 2 electrons can be there. Energy level 2, 8 electrons can be there. Energy level 3, 8 electrons can be there. But at one energy state, only 1 electron would be there. Are you able to understand this point? So this is what I have written. Energy level is like a floor. Imagine a building with several floors. Each floor represents a specific amount of energy that electrons can have. Okay. So n equals to 1 will have a specific amount of energy. Now what is this energy state? It is like a room on the floor. So each floor can have many rooms. Each room is a specific position an electron can occupy at that energy. So on this energy level, this is like a specific position that electron is occupying. So this is known as energy state. So energy level and energy state both are complete different thing. Are you able to understand this point? So example also I have given. Floor 1 is energy level 1. Room 1 on floor 1 is like energy state 1. Room 2 on floor 1 is like energy state 2. So electrons can be on the same floor. That means electron can have the same energy level, but it has to be there in the different energy state. Same energy level but different energy state, and according to Pauli's exclusion principle, you don't even need to remember the name of the scientist. Only thing you need to remember is that in one energy state only one electron can lie. In one energy state only one electron can lie of opposite spin, of the same spin, of the same spin. But spinning and all these things is not important, although this subject should be understood by the quantum mechanics. Okay, but we are not going to understand quantum mechanics here, because quantum mechanics, if you need to understand, that means you should have taken engineering physics, but you are studying electronics engineering. Okay, so quantum mechanics and everything you will study if you do your research into the devices. In future, after clearing the gate examination, if you go for masters or PhD in devices only, then you will understand this subject from the quantum mechanics part. So we will start by the psi function there. Okay, so from that kind of that we will start. Probability distribution function. So from there they will start. But here we are understanding on the top level only. So there you will understand the meaning of opposite spin and same spin. Right? So from this slide, what do you understand? On one particular energy state, only one electron will be there. That's it. This is what you understand from this particular slide. Okay. Now there is something called electronic configuration. Now you might be thinking that, sir, we are studying discrete topics. Like first we understood the meaning of energy, then sir, this energy of hydrogen atom came into action. Then in between we are studying energy level and energy state. Now we are studying electronic configuration. So everything will make sense. You need to have some patience. Okay, everything combined will make sense. Just have some patience. So there is something called electronic configuration, which you might have studied in class 11, 12th chemistry. Even if you did not study, don't worry. So in hydrogen atom there is only one electron. So this is how I will represent it, 1s1. So 1s is like a energy level. 1s is like a energy level. In this energy level there is only one electron. And silicon atom, what is the atomic number of silicon atom? That is 14. So there will be 14 electrons. So 1s2, 2s2, 2p6, 3s2, 3p2. So this s is like an energy level. This energy level can have 2 electrons. This p is like an energy level. This p can have 6 electrons. This s is an energy level. This is like a floor. This is also one floor. On this floor 2 rooms are available. On this floor 6 rooms are available. In this hydrogen atom, in this particular floor 2 rooms are available, no? So out of these 2 rooms only one room is filled. On this particular floor 6 rooms are available. Out of these 6 rooms, here 2 rooms are completely filled, 2 rooms are completely filled, 6 rooms are completely filled, but look at this side. So 2 rooms are completely filled, but here 6 rooms are available. Out of these 6 rooms only 2 rooms are filled. So always we will care about the outermost cell. What I am saying, always we will care about the outermost cell. So this is the outermost cell here. These 4 electrons are the free electrons. What I mean to say is that, let's just say this was our nucleus. Then this was n equals to 1, n equals to 2, n equals to 3. Okay. So here there were 2 electrons. Then 8 electrons were there. 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then 4 electrons. Now these 4 electrons can make the bond with the other atom. Let's just say these 2 atoms come closer, then this electron and this electron can make the bond. These electrons are near to the nucleus. So they are bound by the nucleus, but they are farther away from the nucleus. That means they are more free. So who will be contributing in making the bond? Why we are caring about making the bond? Because now we have studied about atom, right? We have already studied about atom. This is one atom. Now what we will do? We need to make the material. What is our target? Our target is making the material. So now we need to take atoms closer. One atom is here, one atom is here. Two atoms are very farther away, they will not make any material. If I want to make the material, I need to take the atoms closer, right? If I need to take the atoms closer, then what will happen? These electrons will be influenced by these electrons. Previously, here what I have written, isolated hydrogen atom. That means this hydrogen atom which is not in the influence of any other hydrogen atom. So this electron is getting only one force, that is through this nucleus, that's it. This electron and this electron is not making any force. This nucleus, this electron not making any force. This nucleus, this electron not making any force. This nucleus not making any force. That means they are isolated, that means they are further away, they are far, there is very huge distance between both of them. So if there is huge distance between both of them, that means they are not going to make any bonding, and if they are not closer to each other, there is no bonding, that means there will not be any material. To make the material, we need to take them closer. So which electron I will be caring about? I will be caring about the outermost electrons. So I will be caring about these two electrons, and these outermost electrons are present in the outermost shell, outermost energy level. So this outermost energy level is known as valence shell. Okay, what this is known as? Valence shell. Okay, so these outermost energy level is known as valence shell. Here what is the valence shell? Here only one electron is there, so this is the valence shell. So my major matter of concern will be towards the valence shell. Okay, so I will be caring about these 4 electrons when I consider silicon. When I am considering hydrogen, I will be caring about this 1 electron. Now what I am doing is that I am bringing 2 hydrogen atoms together. Why I am doing so? Because I need to make the material. So previously hydrogen atoms were further away. So now I am making a graph. What graph I am making? I am plotting electron energy versus interatomic distance. What is the meaning here? The meaning is, when they are further away, when these two hydrogen atoms are further away, that means distance is very large. That means you are somewhere here. The distance is very large. When the distance is very large, at that time this electron is not getting affected by this electron. This electron is not getting affected by this nucleus. This nucleus is not getting affected by this electron and this nucleus. Basically, this electron is only feeling the force of this nucleus, and this electron is only feeling the force of this nucleus. That's it. So if they are farther away, so what will be the energy of this particular electron? It would be minus 13.6 divided by n square electron volt. And what will be the energy of this electron? Minus 13.6 divided by n square electron volt. So both will have the same energy, and both are on the same floor. What is that floor? That floor is 1s. Listen to me very carefully, otherwise you will not be able to understand. So both of the electrons are on the same floor. That floor is known as 1s. Both electrons are here. Now you let me know how many rooms are available on this 1s floor. On this 1s floor, how many rooms are available? So for one hydrogen atom, in 1s floor there are 2 rooms, and for other hydrogen atom on 1s floor there are 2 rooms. So here there are actual 4 rooms available. Like, what did I make here? This is the energy I am plotting. And this is the interatomic distance. Like this distance could be some r0 distance. This distance is r0. So at the r0 distance, they are not getting affected by each other. That means both electrons are having the same energy. That could be anything, minus 13.6 divided by n square electron volt, minus 13.6 divided by n square electron volt. Now I am saying that this 1s floor is actually having 4 rooms. Do you understand this point? Why 4 rooms? 1s actually has 2 rooms only. 1s actually has 2 rooms, and P actually has 6 rooms. Okay, P will actually have 6 rooms, S will actually have 2 rooms. But since there are 2 1s floor, this one has floor, this one has floor, but we have to make the same level because they are having the same energy. So in 1s floor there are 2 rooms, so there are 2 1s floor, so there will be total 4 rooms. That means in this 1s floor there are 4 energy state. Did you understand this point or not? A very important point. This is one energy level, but in this one energy level there are 4 energy state. Did you understand this point or not? And since the hydrogen atom are far away, their energy of this electron is same. But now what will happen? We are reducing the difference between these two atoms. What we are doing? We are reducing the distance between these two atoms. Reducing the difference between these two atoms, that means on the graph we will be moving in this direction because interatomic distance is being reduced. Interatomic distance is being reduced. What does that mean? That means you are moving in this direction. So as you move in this direction, what will happen? Now this electron will start getting influenced by these electrons. This nucleus will start putting some force on this electron. This nucleus will start putting some force on these electrons. So now the electron energy will change. So there were total 4 rooms. In one room this electron was lying, in one room this electron was lying. When they were far away, they had no problem. But just as they came closer, just as they started coming closer, then their energy level will split. What will happen? Energy level will start splitting. So here there were 4 energy states. Here there were 4 energy states available. As the distance decreases, so what will happen is that the atoms will say that our energy is changing now. So previously this was our energy, but as the distance changed, as they are coming closer, they are being influenced by the other electrons, and since they are being influenced by the other electrons, their energy will change. So at this particular time their energy was this much. Now the energy will change. Sir, it will reduce or it will get higher, you don't know. The energy will change. That thing you know. The energy will change. So there were total 4 rooms. Now these 4 rooms are splitted. Initially all 4 rooms were on the same level, but since the atoms are coming closer, their energy are getting changed, and now these 4 rooms are split. These 4 rooms are split in this manner. Now I will tell a statement that you need to remember, that electrons are lazy. Electrons are lazy. How many electrons you are having? 4 energy states are there and 2 electrons you are having. So electrons are lazy, so they will always occupy the lower energy state. So these 2 electrons will come here. Electrons are lazy, they will always occupy the lower energy state. So there were total 4 states. All states were there at the same level, but just as the atoms came closer, these electrons were getting influenced by the nucleus of the other atom, along with that the electron of the other atom as well. So previously this electron was getting a force of only this electron, but now this electron is getting a force of this electron, this nucleus and this nucleus. So 3 forces are acting upon it, so their energy will change. So if their energy is, it's like you can understand by an analogy that initially you guys were living on the same floor. Okay, this was the floor of your hostel room. You were living on the same floor, but you were far away. You were not friends, neither friends nor enemy. But just as you started getting closer, you got to know strange thing about each other, right? Like this guy drinks a lot, this guy smokes a lot, this guy studies a lot. So you guys got to know strange things about each other. So just as you guys started coming closer, you got to know that we have to take rooms on the different floor. Or what you will do, you will take up your complete room and you will move to the different floors. So there were actually 4 rooms. 2 rooms were empty and 2 rooms were filled. So on one level only there were 4 rooms, but what you did, you just took the rooms on the different floors now. You just took the complete room, you made a different floor. You took the complete room, you made a different floor. This room also made a different floor, this room also made a different floor. But you guys are lazy, you will occupy the lower energy states. So there are 4 energy states. Out of these 4 energy states, you will occupy the lower energy state. Are you able to understand this point or not? Okay. Sir, what will be the structure? like how this energy level structure is like this only, why it is not like this. So all these structures are understood by the differential equation, by the quantum mechanics. So with respect to psi function, you will solve a second order differential equation, and then you will get all this theory. Like all these theories are understood by quantum mechanics only, but you don't need to study quantum mechanics. If I start teaching quantum mechanics, then you will lose the interest here only. You will feel like that EDC is very difficult. So that part we are not going into, right? So that's why in the easiest possible manner I am trying to explain this particular concept. Okay, once you get into research, like in the industry these works are not there. Like if you get a job, then in the job you might not be doing research on devices, you might be working on circuits only. But once you get into some good college or some good university for your research, then the research would be based on devices. Okay, so there you will understand everything right from the scratch, from quantum mechanics only. But as of now you will understand in this manner only. So just as the atom started coming closer, the electron of the atom are getting influenced by the nucleus of the particular atom and the nucleus of the other atom and the electron of the other atom. Then their energy is getting changed. So energy levels are splitting. You are getting 4 energy state. Out of these 4 energy state, 2 energy states are filled. 2 filled energy state and 2 energy states are empty. To empty energy state. So just as you keep on reducing the difference, just as you keep on reducing the distance, okay, just as you keep on reducing this distance, there will be one equilibrium distance. At that particular distance, the bond will be made. Are you able to understand this point? Like when they were further away, there was no bond. Coming closer, 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 at one distance, at one particular distance, there will be a stable bond, and that will be more than enough to make a material. So only 2 atoms will never make the material. This is just we are understanding by the example of 2 atoms. Like there will be a lot of atoms. You will keep on taking the atoms closer and closer. Are you able to understand this point? As of now, we are understanding only with respect to 2 atoms. When we study silicon, we will understand with respect to n atoms. First, we will understand with respect to 2 atoms. Then we will understand with respect to n atoms. So as they keep on coming together, the energy levels will. Then there will be a lot of energy states, right? So a lot of energy level will be splitted into energy states. The lowest energy states will be occupied by the electrons, and the higher energy states will not be occupied by the electrons. They will be empty, and there will be one distance. Let's just say this is the equilibrium distance. What I am saying, let's just say this is the equilibrium distance. So there will be one equilibrium distance where the bond will be made. Let's just say this is the equilibrium distance. So I am calling this distance as A naught. So at that particular distance, the bond will be made, and that would be enough to make the material. So did you understand this analogy? We have given the theory as well. When many hydrogen atoms are brought close together to form a solid, the outermost electron of each atom begin to interact with the electrons and the nuclei of the neighboring atom. This interaction slightly shift the allowed energy of each electron, because the Pauli exclusion principle states that no two electron in the entire system can have the exact same energy state. So I told you on one energy state only one electron can be present. So it's not that sir 2 electrons are there, so they will be lying on the same energy state. No, they cannot lie on the same energy state. In one energy state only one electron would be there. So this is what I have written here. As a result, the single discrete level of an isolated hydrogen atom splits into a large number of closely spaced level. Okay, so this is single level has been splitted into the closely spaced energy levels. And this closely spaced energy level is known as energy band. Okay, so this continuous range of frequency is known as energy band. Sorry, not frequency. This continuous range of energy is known as energy band. This continuous range of energy is known as energy band. So a lot of energy states are there. So a lot of energy states are there, and the distance between these energy states is very low. This distance between these energy states will be very low. Okay, so this is known as energy band. Combined we call it energy band. Okay. Thus, in a solid made from hydrogen atom, the original discrete atomic level give rise to a structure of continuous energy bands due to atomic interaction, and this is the same fundamental mechanism of band formation in all solids. So now we will understand it with respect to silicon. Why silicon? Because silicon will give you a semiconductor. So the same theory that we have understood for hydrogen, the same theory we will understand for silicon now. Okay, the same theory we will study for silicon. Is that clear to you? So I hope till this point we have spent 1 hour here. So in this 1 hour, like in the examination, it might not be useful for you, but to understand the subject, you should be at least understanding that how semiconductors are made, how a particular material is made. That there would be one material. In the material, what will happen? There will be atoms. In the atom, there will be nucleus and there will be electron. Then we understood about the energy of the electron, and then we understood that if we are bringing two atoms together, then what is happening? They are framing a energy band. They are framing energy bands in the lower most energy states. The electrons are occupied. So there are a lot of energy states. The electrons will be occupying the states of lowest energy. So these are the state of lowest energy, because I told you as we go upward, the energy will increase. So they are occupying the lowest energy states. Is that clear to you? Now similar analogy we are going to understand for silicon. But before that, I will take a break, drink some water, and then I will come back. So you can also drink some water, and then we will start studying the similar theory for silicon atoms. So in the silicon atoms, who will be our matter of concern? They will be our matter of concern because they are the valence shell. So in n equals to 1, there are 2 electrons. In n equals to 2, there are 8 electrons. And then this is the S energy level, this is the P energy level, 2 electrons, 2 electrons. So they will be there to make the bonds. So these 2 energy level will be making the bonds, right? So they are our matter of concern. So we will understand the theory. What we will do is that first we will bring 2 silicon atoms together, and then we will see what happens. So here there was only one valence shell, that was 1s, but here there are 2 valence shells, 3s and 3p. So let's see what happens. Okay then, yeah. So let me take a break and then I will come back. Yeah, welcome back guys. So we need to study about energy band formation in silicon now. So what is energy band? Energy band means these continuous energy states, right? So when you see these energy states are continuous, so these continuous energy states are collectively they are known as energy bands. So same kind of energy band that we have studied in the hydrogen atom, the same kind of energy band will be made in the silicon atoms as well, with respect to the silicon atoms as well. So this is one silicon atom. Now what we are going to do is that we are going to bring 2 silicon atoms together. So this is one silicon atom, this is another silicon atom. In the outermost shell, you are having 4 electrons. In silicon, in the outermost shell, you are having 4 electrons. So only outermost shell I am making, okay? And surely there is nucleus. 4 electrons we are having. So only the outermost shell we are making. Interatomic distance, initially they are farther away. So if they are farther away, that means these 4 electrons, everyone will have the same energy level. Not everyone will have the same energy level. Like in 3s there are 2 electrons, right? And in 3p there are 2 electrons. So 3s will have the same energy level and 3p will have the same energy level, right? So 3s will have the same energy level and 3p will have the same energy level. Although these will be very nearer, okay? Here the distance will be very low, right? But still we are making it farther. So whatever the electrons are there in the 3s energy level and whatever the electrons that are there in the 3p energy level, so they will have the same energy and they will have the same energy. So in 3s, for one silicon atom in 3s there are 2 electrons. So for 2 silicon atom in 3s there will be 4 electrons. Say yes or no? And for one silicon atom in 3p there are 2 electrons. Then for 2 silicon atoms in 3p there will be 4 electrons. For 2 silicon atoms, we are making it for the 2 silicon atom. We are bringing 2 silicon atoms together. We are plotting electron energy with respect to interatomic distance. As of now, the interatomic distance is very high. That means they are very farther away. If they are farther away, that means this electron is also influenced by this nucleus only. This electron, this nucleus, this electron, this nucleus, this electron, this nucleus. Although they are in the slightly different energy level. Like this is known as n equals to 3 only. This is your n equals to 3 level only. This is your n equals to 3 level only. But in n equals to 3 level, there are two orbits, s orbit and p orbit, s orbital and p orbital. Okay, so they have slightly different energy level. Slightly different energy levels are there. So it might happen that these two these two are having different energy and these two are having different energy, almost nearly the same energy level they will have. Okay, and since they are not influenced by each other, so they will have the same energy. So whatever that are available in 3s, they will have the same energy, and whatever that are available in 3p, they will also have the same energy. So total 4 electrons here, 4 electrons here, so total 4 here and 4 here. 8 electrons are there. Is that clear to you? Now, how many states are there in 3p? So 3p, one level of 3p have 6 rooms. One level of 3p have 6 rooms. Out of these 6 rooms, only 2 are filled. Other level of 3p also have the 6 rooms. Out of these 6 rooms, only 2 are filled. So there, in this particular scenario, 2 atoms are coming closer. That means total 12 energy states are there, total 12 rooms are there. Out of these energy states, how many states are filled? 4 filled energy states. Do you agree to this point? What about 3s? In 3s, how many rooms are there? 2. For one atom, for the other atom as well. For one atom, for the other atom as well, 2 rooms are there. In this atom, 2 electrons are filled. Here also, 2 electrons are filled. So total 4 energy states are there. And all 4 are filled. So total 12 energy states were there in the 3p floor. On the 3p floor, 6 rooms, 6 rooms. Total 12 rooms were there, only 4 were filled. On 3s floor, 2 rooms, 2 rooms. Total 4 rooms were there, all 4 were completely filled. So total energy states are 12 plus 4, 16. Out of those, 8 states are filled. Now what will happen is that they will start coming together. And as they start coming, they will start coming nearer. So if they are coming nearer, then what will happen is that these electrons will get started influenced by this nucleus and these electrons. So now the energy of these electrons will change. So energy level will start splitting. So what will happen is that this energy level will start splitting in this manner, and this energy level will also start splitting in this manner. At some point of time, they will become one energy level only. Like they will merge these two energy level, you can say, or better I should have said energy states. So these energy states have started splitting now. These energy states have started splitting now. At one point of time, they will become together, but after that they will split again. So this kind of energy level splitting you will get. A rough diagram I have made. Sir, how do you get the complete idea of this diagram? So complete idea of this diagram you will get from the wave function. But on a brief level, you can see what really happened. The energy level started splitting. Energy level or energy states started splitting. So this is going like this only. Basically, like this energy level has started splitting in this manner, right? And this energy level has started splitting in this manner. So what you can see is that first they are merging here, and then it is being separated again. This guy is going here and this guy is going here. Like first they will merge and then they will be separated again. Are you able to understand this point? Like, sir, how this kind of waveform only came? Sir, how in this manner only they are splitting? So everything will be explained when you solve this second order differential equation of wave function, of phi function, of this xi function, of this wave function. When you solve the second order differential equation, then this waveform will come. But on the crude level, on the surface level, you just need to see that as they are coming together, that means they are being influenced by each other's nucleus and electrons, and then their energy level will split, right? So now you let me know how many total states are there. 12 here and 4 here. So total energy states are 16. 12 energy states of this one, 4 energy state of this one. So total energy states are 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Total energy states are 16. Out of these 16 energy states, 8 energy states are filled. 4 plus 4, 8 energy states are filled. So 1, 2, 3, 4, 5, 6, 7, 8. Why I am starting from the bottom? Because I told you electrons will always occupy the lower energy states. And then again it is splitted. So when again it is splitted, what really happens is that 8 energy states will be downward and 8 energy states will be upward. Out of these energy states, out of these 16 energy states, 8 energy states are filled. And now this particular distance that we are getting, this particular distance is the equilibrium distance. So this I am calling as A naught. Like when you have taken these two atoms at A naught distance, at that time they will frame the bond. Like what I was doing, I was reducing the interatomic distance, started from here, reducing. Just as the distance has become A naught, at that time you will see that yes, silicon crystal has been made. What do you mean by silicon crystal? That means silicon. Here we are talking about only 2 atoms, but we will talk about n atoms as well. So those silicon atoms will keep on coming closer. So then they will frame this kind of silicon crystal. So a lot of silicon atoms will come together, they will make the bond. This bond is known as covalent bond. So this silicon crystal will be made. So this would be the equilibrium distance. Are you able to understand this point? So this is known as equilibrium distance. So did you understand what is happening here? The only confusion part would be there that sir, first they are merging and then they are splitting. First the energy level, this was the here all the electrons were there in the same energy level, all the electrons were there in the same energy level. Then what really happened is that both of the energy level splitted into energy states. Now first the energy states were merged and then they were splitted again. So this analogy we cannot explain. Actually here what really happens is that the bond is very weak. Silicon atoms are coming closer, they will frame a bond. Here as well they will frame a bond, but that bond is very weak. But once you reach here, this bond is stronger. And this is the equilibrium state. So first they will merge and then they will split. There is no reasoning. You cannot, like there is reasoning, but I cannot explain it here. Are you able to understand this point? So total states 12 here, 4 here, total 16 energy states were there. Out of those only 8 rooms were filled. Out of those 16 rooms only 8 rooms were filled and electrons will occupy the lowest energy rooms, or you can say lowest energy states. Okay, so this is what is happening. Now these lowest energy states are known as, now energy states, these are very continuous energy states, no? Like these are 8 energy states. Similarly here you made 4 energy states, they were very continuous. So collectively what I called energy band. So collectively here as well what you will call energy band. So these energy states and these energy states, the energy states which are there at a very minute distance, at a very lesser distance, that means this energy state, then this energy state, this energy state, this energy state, this energy state, they are at a very less distance, so they are known as energy band. Okay, energy band. So now this band will be known as valence band and this band will be known as conduction band. Why this is known as valence band? Because all the valence shell electrons are coming here only. All the valence shell electrons, 2 plus 2 4, 4 electrons of one atom and 4 electrons of other atom. So total 8 electrons, all the 8 electrons are coming in this energy band. So if all the 8 electrons are coming in this energy band, then this energy band is known as valence band. What it is known as? Valence band. And this is known as conduction band. Sir, why the name is conduction? You will understand it. When we study the semiconductor, when we study the working of semiconductor, you will understand why we call it conduction band. Because if the electron reaches here, if the electron reaches in this energy band, then it will conduct the current. That's why it is known as conduction band. Sir, how it will conduct the current, that we will see. But as of now, what you need to see is that all the valence shell electrons are being occupied by this energy band. That's why it is known as valence band. Other electrons, if the electrons reaches here, if the electrons reaches in this energy band, then it will conduct the current. That's why this energy band is known as conduction band. and the gap between conduction band and the valence band, the gap between the lowest energy level of the conduction band and highest energy level of the valence band, this is known as forbidden energy gap, or it is known as band gap. All the theory will be written, don't worry about that. What I am saying, the gap between the lowest energy level of the conduction band and highest energy level of the valence band, that is known as band gap, or it is known as forbidden energy gap. All good? More points are there, we will see one by one, but as of now, in conclusion or in summary, what do you understand? You are having 4 valence shell electrons, 2 electrons were there in the s orbit, 2 electrons were there in the p orbit. Both of them were having nearly the same energy, Now you are bringing 2 silicon atoms together, that means 4 electrons in 3s, 4 electrons in 3p, but 3p can have 12 energy states and 3s can have 4 energy states. All electrons are filled here, 4 filled energy states are there, 8 empty energy states are there. Since the electrons are coming together, they are being influenced by the nucleus and electrons of the other atom. Since they are being influenced by the nucleus and electron of the other atom, their energy of a particular electron will change. So the energy level will split into energy states. These energy states are continuous, that's why it is known as energy bands. Electrons will occupy the lowest energy level of the energy band. Further, they are again split into different energy bands. The energy band which is occupied by the valence shell electrons, that is known as valence band, which is completely filled, and other band is known as conduction band, which is completely empty. Is that clear to you? So this is the complete theory of bringing 2 silicon atoms together. If I bring n silicon atoms together, then this will be the scenario. So just let me know one thing. If I bring n silicon atoms together, so this will also have 3p orbit and 3s orbit would be there. In one silicon atom, 3s orbit has how many rooms? 2 rooms. 3s orbit will have 2 rooms. So in n silicon atoms, 3s will have 2n rooms. So 2n states are there. What is the electronic configuration? 3s2, 3p2. So all the 2 rooms are filled. So here also all the rooms will be filled. So 2n states are there, 2n electrons have been there. All the 2n states are filled with the electrons. What about 3p? In 3p, in one silicon atom, how many rooms are there? In one silicon atoms, 3 rooms are there. That means, 6 rooms are there. That means 6 energy states is there. In 3p, for one silicon atoms, 6 energy states are there. For n silicon atom, how many energy states would be there? For n silicon atom, 6n energy state would be there. What is the electronic configuration? 3p2. Out of these 6 states, only 2 states are filled. In one silicon atoms, 2 states are filled. So in n silicon atoms, 2n states would be filled. So 2n electrons are there. So total 8n states. Total states are 8n. Filled states are, how many filled states are there? Filled states are 2n, 2n, 4n. 4n filled states are there. Is that clear to you? Is this theory clear to you? You can simply relate it with the previous diagram. Here n was 2. In this particular diagram, n was 2. So 16 total states were there, 8 were filled. 12 states were there, 4 were filled. You can see 12 states were there, 4 were filled. Here n equals to 2, you put 4 states were there, 4 were filled. 4 states were there, 4 were filled. Now if they are coming together, then what will happen? First they will be merging, all the states will be merging. First the states are split. States are split, right? States are split, and then they again merged. So here they are split, and then they merged. Here they merged, and then again split, right? So here total 4n states will come into action. When n was equals to 2, here total 8 states came, right? 8 filled state, 4 filled state, 4 filled state. So total 8 filled states are there. So in the similar manner, here total 4n states would be there and all the states will be filled. So 4n states with 4n electrons. So here total 4n states would be there. Total 4n states would be there and every state will be filled with the electron. Every state will be filled with the electron. And here also total 4n states would be there and all the states will be empty. And this is known as lowest point of the conduction band, lowest energy point of the conduction band, and this is the highest energy of the valence band. And the difference between the lowest energy level of the conduction band and highest energy level of the valence band is known as forbidden energy gap. Are you able to understand this point or not? Whatever the example, whatever the time that I have spent for 2 silicon atom, the same time, the same theory is there for n silicon atom as well. Is that clear to you or not? I hope it is clear. I don't think that I need to explain this, how this 4n state came into action, how this 0 electrons came into action. I hope everything is clear. Total states available were 8n states. Out of those, 4n states were filled. When energy level split into energy states, energy level were split into energy states. Then it was merged and then again splitted into the energy states. Now electrons will occupy the lowest energy state. Electrons will occupy the lowest energy states. So these are the lowest energy states. So how it is split? It is split in a manner that 4n states come downward and 4n states goes upward. So 4n states are having higher energy, 4n states are having lower energy. And electrons will occupy the lower energy states. And since these energy states are closely spaced, since these energy states are continuous, that's why it is known as energy bands. And now all the valence shell electrons are coming in this particular energy band. So this energy band is known as valence band. Okay, and if the electron reaches from here to this particular energy band, if the electron reaches from valence band to this particular energy band, then our semiconductor will conduct the current, and that's why this band is known as conduction band. Okay, so this uses of conduction band we will study later on, but as of now what you are able to understand, that energy levels are split into two bands, valence band and the conduction band. So let me make the valence band and the conduction band. So how will I make it? So what you can see is that this is the bottom of the conduction band and this is the top of the conduction band. This is the top of the valence band and this is the bottom of the valence band. And here there are states, 4n states here. So I am making 4 states only, 4n states are there, so I am making 4 states. And here also 4 states I am making. Here also total 4n states. Out of these 4n states, all the states are filled with electron. All the states are filled with electron. But these states are completely empty. This is known as conduction band. What this is known as? Conduction band. And this is known as valence band. The lowest energy level of the conduction band is shown by EC. Okay, lowest energy level of the conduction band is shown by EC. The highest energy level of the valence band is shown by EV. The energy gap between both of them is shown by forbidden energy gap, EC minus EV. Okay, well and good. Sir, how this conduction band, and this phenomena is known as band diagram. So sir, why this band diagram is important? You will slowly understand. Okay, now we are moving towards a semiconductor. So slowly you will understand that, sir, why this band diagram is important. But did you understand this band diagram? Like, this is a very typical theory which we are understanding in the simplest words possible. Okay, now we will relate the band diagram and the crystal structure. What do you mean by crystal structure, sir? Like, there would be silicon atoms, no? 1 silicon atom, 2 silicon atoms, and 3 silicon atom, 4 silicon atoms. Now they are coming closer. So n silicon atoms are coming closer, no? Right? These n silicon atoms are coming closer. So let's just say this was 1 silicon atom. This silicon atom, in the outermost shell, it was having 4 electrons. This was another silicon atom, again in the outermost shell having 4 electrons. another silicon atoms outermost shell having 4 electrons. Again there is silicon atoms outermost shell having 4 electrons. Again silicon atom outermost shell having 4 electrons, and they are making the bond. They are making this covalent bond. These 4 electrons, 4 electrons, 4 electrons, they are making the covalent bond. Now these electrons will also make the covalent bond from some other silicon atom. This will also make the covalent bond. This will also make the covalent bond. All these silicon atoms will make the covalent bond with the other silicon atoms. So a lot of silicon atoms would be there, and silicon atoms are there which are making the covalent bond. Okay. Now this diagram, this is the crystal structure of silicon. This will be there in the 3D. So in the this we are looking in 2D. So in the 3D it would be there actually. Okay. So this is diamond structure would be there, which will be there in the 3D. So what kind of structure would be there, that you don't need to care about. Just telling that this structure will be there in the 3D. Now we are able to, now we will relate it to Venn diagram. What do you mean by Venn diagram? In Venn diagram there are two kind of bands, valence band and the conduction band. Valence band and the conduction band. So this was the valence band, this was the conduction band. Both of the bands are having the same number of states, but here all the states are filled and here all the states are empty. So if I interrelate, what is the meaning here? Like here, do you see any free electron? This guy was having 4 electrons, all the 4 electrons are making the bonds with the other electron. This guy is having 4 electrons, all the 4 electrons are making bond with the other electron. 4 electrons, all are making bond with the other electron. So there is no free electron. There is no free electron, that means all the electrons are present in the valence band only. Are you able to understand this point? There is no free electron available. That means all the electrons are present in the valence band. So whenever I say there is no free electrons, there are bound electrons. So all the bound electrons are shown in the valence band. So all the bound electrons are having the lowest energy. Why they are having the lowest energy? Because they are bound, right? If they were free, that means they were having higher energy. So by any means, if they become free, that means they will go from valence band to conduction band. This is the meaning, like this is how you can relate the band structure, this band diagram with crystal structure. Like electrons are there in the valence band. What is the meaning of that? The meaning is that all the electrons are bound. They are making the bond. But what if this electron gets free? This electron gets some energy and it gets free. That means how I will show it, that this electron has gone to this place. Are you able to understand this point? So again and again this theory will come up and you will be able to understand it. Don't worry about that. Again and again when we study intrinsic semiconductor, extrinsic semiconductor, again and again I will be making this crystal structure and this band diagram, and again I will be interrelating it. So slowly you will understand more, but as of now, this is the scenario that silicon, everywhere silicon would be there. 4 electrons are there, all are making the bond. That means all are bound. No free electrons are there. So if there is no free electrons, that means there is no electron in the conduction band. All are bound, that means all electrons are there in the valence band. So this is the meaning of this diagram actually. Okay. So total you are having 4n electrons. All the 4n electrons went into valence band. That means all the 4n electrons are making the bond. No free electron is there. If there was any free electron, then it would have occupied the conduction band, not the valence band. What do you mean by band? Continuous energy states are known as band. Continuous energy states, since these energy states are having very lesser gap. If it was having larger gap, then it would not be called valence band, but they are having very lesser gap, that's why it is known as bands. Okay. Now since all the valence shell electrons are coming in the lowest energy band, that's why it is known as valence band, and it is known as conduction band. So this complete theory I have written. So in the whole EDC, I will make sure that you get the best possible theory in the best possible language. So very easy language, you will be able to understand everything. So let's read it out. A single isolated silicon atom has well defined electron energy levels 3s and 3p. 3p is written there. 3s level can hold 2 electrons and 3p can hold 6 electrons. Now 3s orbital has 2n states, because if n silicon atoms, if we talk about n silicon atoms, then 3s orbital will have 2n states and 3p orbital will have 6n states. When many silicon atoms are brought closer together to make a crystal, these states will further split into very closely spaced levels due to interaction between neighboring atoms. You understood this part? Like if there is interaction between the neighboring atoms, that means one electron is putting some force on the other electron. One nucleus is putting some force on the other electron, right? Forming two distinct energy band. The lower energy band is known as valence band with the 4n fully filled energy states at 0 Kelvin. Okay, so everything we are talking about at 0 Kelvin, 0 Kelvin temperature. Okay, and the upper band is known as conduction band with 4n empty states at 0 Kelvin. So these states are empty, these states are completely filled. Separated by an energy gap where no electron can exist. So first I will mark these lines: conduction band, 4n fully filled energy states at 0 Kelvin in the valence band, and in the conduction band 4n empty states. Okay, separated by an energy gap where no electrons can exist, and this energy gap is known as forbidden energy gap. Okay, for silicon this energy gap is 1.1 electron volts at room temperature. Approximately it is 1.1 electron volt at room temperature. This energy gap at room temperature for silicon, this energy gap is approximately 1.1 electron volt. Okay. Okay. So all these theory I have again written. This is the conduction band, this is the valence band. Energy band diagram for semiconductors I have made. Conduction band, valence band. Lowest energy level of the conduction band is known as EC. EV is known as highest energy level of the valence band. And forbidden energy gap is now given as EC minus EV. Let's just say this EC was 10 electron volt and this EV was 9 electron volt. Then EG would have been 1 electron volt. Okay. Now you would see that this diagram I have made, then one energy state, then other energy state, and then what I have done is that these energy states are very near. Here also I have done this one energy state, another energy state, and then the energy states I am making very near. So like sir, how it happens, that knowledge you will not have. For that you would require very higher order mathematics. So you just need to remember one thing, that as you go higher in the conduction band, the effective density of the states increases. That means if I go higher, then here the density of states are increasing. What do you mean by density of states? The number of states are higher here, and here also the number of states are higher. So as I go lower in the valence band, the number of states will become higher. The effective density of the states will increase. So this point you just need to remember, nothing else. No mathematics is required that sir, if I go higher, why the number of states are increasing? No one will ask you that. Just if you see this kind of diagram anywhere, you should know that as we go higher in the conduction band, the effective density of the states will increase. As we go lower in the valence band, the effective density of the states will increase. Okay, and this density of state, this effective density of state, this DOS concept will also come into action when we study Fermi direct distribution. So when we study Fermi direct distribution, this concept will again come into action, and again I will discuss it. But there also I will tell you only one point, that the density of state will increase as you go higher in the conduction band, and density of states will decrease as we go lower in the valence band. But when I am explaining the theory, look, here I was explaining the theory, so here I made the density same. At all the point I made the density same. So it might happen that even in the textbook as well, even in a lot of NPTEL lectures as well, you will see that educators or professor will make the energy levels same only. Like the density of states they will make same. So just for the explanation purpose they can make it. Okay, just for the explanation purpose they can make the energy levels in this manner, energy states in this manner. So don't think that sir you are drawing it wrong. Just for the sake of understanding they can draw in this manner. Just for the sake of understanding they can draw in this manner. But actual diagram will be like this. Actual diagram will be like this. As we go higher, the density of states will increase. As we go here, as we go lower, the density of states will increase. Okay. Okay then. Now some important points we will discuss, and then we will again come back to our theory. Okay. So as of now, what we have built up? We have built up this kind of silicon crystal. And in this silicon crystal at 0 Kelvin, everything is happening at 0 Kelvin. That means there is no temperature, there is 0 Kelvin temperature. So everything is happening at 0 Kelvin temperature. So at 0 Kelvin temperature, this is the scenario that valence band is completely filled and conduction band is completely empty, because all the electrons are bound. They are making the covalent bond, no electrons is free. Okay. But before that, before understanding the silicon crystal again, we need to understand some points, some very basic point which you might already be knowing. So some very basic point we are going to understand. So this is some material. It could be silicon material, it could be anything. So this is some a random material. In this material, there is a free electron. In this material, there is a free electron. What it is? It is a free electron. Now, what I did, I took this material, I connected some wire and I gave it some supply. I gave a supply of V0 voltage. What I did, I gave a supply of V0 voltage. Now, if I say here there is zero potential, then what will be the potential here? V0, right? If this is 0, then this will be V0. Basic network analysis, I hope you know it. So across this material, let's just say this is the material. So across this material, what I have done is that I connected some wire, I gave it some supply of V0 voltage. So here there is V0 voltage and here there is 0 volt. So V0 voltage I can show by positive and 0 volt I can show by negative. So positive and negative. So it's like here there is a positive charge, here there is a negative charge. Let's just say if here there was a minus V0 by 2 potential, then what would be the potential here? Plus V0 by 2. Because let's just say if I am saying that this potential is not 0 volt, this potential is actually minus V0 by 2. So what will be this potential? Minus V0 by 2 plus V0. So what that would be? Plus V0 by 2. So if I am showing this by negative, this I can show by positive, right? Very simple thing. So here I am showing 0, here I am showing V0. So this is positive charge, this is negative charge. Do you know what is the direction of electric field? Direction of electric field is always from the positive charge to negative charge. Electric field lines will always come out from the positive charge and will go into the negative charge. So direction of electric field will always be from positive to negative. Electric field. This is the direction of electric field. This is the direction of electric field. So on this material, this could be material, this could be semiconductor material, this could be conductor, it could be anything. Just I am saying that this material is having some free electrons. This material is having some free electrons. That means here there will be this electric field present. This E field is present. How will I show the electric field? By this sign. I will not show the electric field by this. I will show the electric field by this kind of E. This is the electric field. Now, if you have known some basics of EMFT, then in electric field E, if there is a charge Q present, then what kind of force it will have? That will be Q into E. In this electric field, some charge Q is present, so it will get a force of Q into E. Now, if this charge is positive, then the force on this charge will be in the same direction as the electric field. If this charge is positive, then the force on this, if this charge is positive, then the force on this positive charge will be in the same direction as the electric field. But if this charge is negative, then the force will be opposite to the direction of electric field. So this electron is negatively charged. This electron is negatively charged, right? And then there is an electric field in this direction. So where the electron will feel the force? The electron will feel the force in the opposite direction. So electron will move here. Are you able to understand this point? This material was having a free electron. When it was having a free electron, it was not moving. This electron was not moving. What I did, I connected a battery. Because of this V voltage, there was some potential. Because of this V potential, there was some electric field. This electric field was going from positive to negative. That means it was going from left to right. Because of this electric field, this electron was getting some force. Since it is negatively charged, so it got the force in the opposite direction of the electric field. Now, if you know one thing, if electron is moving in this direction, then the current will be opposite to it. If this is the flow of electron, then this will be the current because of the electron. The current will always flow in the opposite direction of the flow of electron. Very, very basic thing in class 11, 12th or in network analysis you would have studied it. If electron is flowing from right to left, then the current will flow from left to right. That means in this material the current will flow in this direction. So what all points I have written? electrons move opposite to the direction of applied electric field. Electrons will always move. Electrons are negatively charged. That's why they will always move in the opposite direction to the applied electric field. This is the direction of the applied electric field. This is the direction of the applied electric field. So electrons will always move opposite to the direction of applied electric field. For the current to flow, electron must have a net motion. Look, this material was having free electron, but this electron was not moving. This electron was not moving. But what I did, I applied some potential. Because of that, there was electric field. Because of the electric field, there was some force. And if there is some force, that means it will move. So electron started moving. And since the electron is moving, now it will have some current. Now what will be the direction of that current? So the direction of that current would be opposite to the motion of electron. So if electron is moving here, then the direction of current would be this. So direction of current is this. Direction of current is this. So electrons will move here, here, here. Like if I talk electrons, it will move like this. Electrons will move like this. Okay. And the direction of current would be this. This would be the direction of current. This would be the direction of current. So you can see that this is the path of flow of electron. And this is the path of flow of current. So current always flows in the negative direction of the motion of electron. Is this point clear? Sir, why we are studying all these points? You will understand. Okay. You will understand why we are studying all these points. These points are very, very important. But as of now, you just need to see it that yes, we know these points. Now another point is there. We will do the discussion on energy bands. So first I have made a fully filled energy band. That means there are 4 states. All 4 states are filled with the electrons. Empty energy band. There are 4 states. All the states are empty. Partially filled energy band. There are 4 states. Out of these 4 states, 2 states are filled. Okay. Now you look at this point. For the current to flow, electrons must have a net motion. Do you see any electron here? No. If there is no electron, that means there cannot be any current flow. Do you see electrons here? Yes. Can the electrons move? What I am asking, this is a fully filled energy band. Can the electrons move? Where it will move? Can this electron come here? You will say that, sir, this electron can come here. No, it cannot come here. Why is that so? Because Pauli's exclusion principle says that in one energy state, only one electron can be there. So it cannot happen that, sir, this electron will come here. Or it cannot happen that, sir, this electron will go here. So in the fully filled energy band as well, there is no chance for the electron to flow. But what about partially filled energy band? Can this electron move here? Yes, because this room is empty. Let us say in one floor there are 4 rooms. In all the 4 rooms, 4 people are there. In all 4 rooms, 4 people are there. So can the people move? No. Here 4 rooms are there. All 4 rooms are empty. So can the people move? No. Here 4 rooms are there. Out of these 4 rooms, 2 rooms are empty and 2 people are there. 2 people are there in 2 separate rooms. So now those people can move. So this electron can reach here. This electron can go here. So movement of electrons is possible in partially filled energy band. Movement of electron is possible in partially filled energy band. And I told you, for the current to flow, electrons must have a net motion. Here electrons are not having any net motion. Here electrons are not having any net motion. Only in this condition electrons can move. That means only in this condition the current can flow. Whether the current will flow or not, that I don't know. But surely in these conditions current cannot flow. So this is what I have written here. All these points will make sense when we study the silicon crystal. So have patience. So what point is written? If an energy band is completely full or completely empty, no current can flow even if an external electric field is applied. Even if I apply the external electric field and all the bands are completely filled, that means electron cannot move, then current will not flow. Current flows only when the band is partially filled, because then electrons have empty nearby states to move into. They are having empty nearby states to move into. Is this point clear? So whatever the points that we are studying, everything will make sense. Now there is something called thermal energy. Sir, this was a discrete point, like out of the box it came. Sir, this was also a discrete point, out of the box it came. Sir, we were studying silicon crystal everything was making sense here, sir. Suddenly this point, then suddenly sir this point, and suddenly sir this is thermal energy. Sir, why all these things? So all these combined will make sense. You just need to have some patience. Okay. So there is something called thermal energy. So previously, what did I tell you, that how the electron will get the energy? This was the electron. What I did, I gave it some voltage. So it got energy of E into V, right? E into V naught. The electron is accelerated by V naught voltage. So energy was given as Q into V. Electron is having a charge of E into V naught. So it got the energy of E into V naught, right? There is another thing that can give energy to electrons, and that is known as temperature. So because of the temperature as well, the electrons can get some energy. Are you able to understand this point? So that energy is given by that energy is known as thermal energy. The energy of the electron that you are getting because of the temperature. Because of the voltage, electron will get some energy, but because of the temperature as well, the electron can get some energy. So that energy is known as thermal energy, which is given by kT, where K is the Boltzmann constant. The value of Boltzmann constant is, you don't need to remember it. Only thing you need to remember is that thermal energy is proportional to the temperature. Thermal, here I should write thermal energy. So ETH I will write down. This thing you need to remember, that thermal energy is proportional to the temperature. As the temperature increases, electron will get more and more energy. So what do you think, what will be the energy at 0 Kelvin? Thermal energy at 0 Kelvin. So E thermal at 0 Kelvin will be equals to 0 only, right? At 0 Kelvin, the electron will not get any thermal energy. But what is the room's temperature? Room temperature is 27 degrees Celsius. Usually the room temperature is 27 degrees Celsius. In Kelvin, it will be K equals to C plus 273. So that would be 27 plus 273, that would be 300 Kelvin. So your room's temperature is 300 Kelvin. So at the room's temperature, what will be your thermal energy? So that is coming out to be 4.14 into 10 to the power minus 21 joule. Okay. But I will convert it into the electron volt. So for converting it into the electron volt, what I will do, I will divide by 1.6 into 10 to the power minus 19. So that is coming out to be 26 milli electron volt. So at the room's temperature, without even applying any voltage, this is some material I am having. In this material, there is some electrons. In this material, there is some electrons. And this material is there at the room's temperature only. This material is lying in my room, in my table. So whatever the electrons are there in this material, they will already have 26 millivolt energy, or it is nearly equal to 25.9 milli electron volt. So they will have 25.9 milli electron volt energy. So what it will feel like that? What it will feel that they are having 26 milli electron volt energy. It feels that there is some 26 millivolt potential has been applied. Just a second. Yeah. So it will feel that 26 millivolt potential has been applied to the electron. Are you able to understand this point? Electron is having 26 milli electron volt energy at room's temperature, although you are not applying any voltage. But at the room's temperature, it will feel like that the electron is accelerated by this much potential, and this potential is known as thermal voltage. So thermal voltage Vt at room's temperature is given by, approximately it is given by 25.9 millivolt, or sometimes you can take 26 millivolt. This value will be given in the questions. This value will be given, but you should remember it as well. Okay, the thermal voltage Vth you can write down, or Vt you can write down. So the thermal voltage at room's temperature is 26 milli electron volt. What is the meaning of this thermal voltage? Did you understand that? What is the meaning of thermal energy? Without even applying any external voltage source. Here we were applying some external battery. Because of that battery, it was getting a energy of EV naught, right? But that we are not doing here. Just because of the temperature only, it is getting some energy. Just because of the temperature, it is getting some energy. And that energy at room's temperature is coming out to be 25.9 milli electron volt. No value from here you need to remember, only this value you need to remember, 25.9 milli electron volt. Is that clear to you? Okay. And what is thermal voltage? Since the electron is having an energy of 25.9 milli electron volt, it feels like that it is being accelerated by 25.9 millivolt potential difference. That potential difference is known as thermal voltage. Thermal voltage value at room temperature is given by 25.9 millivolt. Is that okay for you? So now everything will make sense, and now we are going to study our silicon crystal that we have already seen. So at 0 Kelvin, we have already seen our silicon crystal. Silicon atoms were there. They were making bonds with the nearby atoms at 0 Kelvin. This was the scenario at 0 Kelvin. This was the scenario at 0 Kelvin. At 0 Kelvin, what did you see? That all the valence band energy states are completely filled. All the energy states are completely filled, and all these conduction band energy states are empty. At 0 Kelvin, is there any thermal voltage present? Is there any thermal energy present? No, there is no thermal energy. Did I apply any battery? No battery I applied. That means no electron is having any energy. No electron is having any energy. That means electrons are not moving. If electrons are not moving, that means the current is 0. At 0 Kelvin, in the silicon crystal, all these electrons are making bonds. What does that mean? All are lying in the valence band, and conduction band is completely empty. Even if I apply any battery here, if I don't apply any battery, is there any chance of current? First thing is that, let's just say there is any material, whether it is conductor or semiconductor or insulator, if you don't apply any battery, then you will never get a current, because you need to give some source, no? You need to give some source. If you give some energy, then only you will get the energy. You cannot create the energy. Energy can never be destroyed. It can never be created. From one mean to other mean, it can be transferred. So if I give voltage energy, then I will get some energy in the electrons. So if I give the energy from my side, then only I will get the energy. So if I am not connecting any battery, then there is no chance of the current flow. But even if you connect the battery, even if at 0 Kelvin I connect the battery, so first question I am asking, is there any thermal energy? No energy is there. If no energy is there, that means these electrons cannot make the transition. These electrons cannot make the transition from here to here. Now if they are not making the transition, then this is the scenario. Now if this is the scenario, then let me know what is this. This band is completely filled, and what is this? This band is completely empty, and this is completely filled. If your bands are completely empty and completely filled, is there any chance of current? No. Right? Where I explained this? Here I explained this. For fully filled energy band and for empty energy band, the current cannot flow even if you are applying the electric field, because electrons are not even having the space to move. So this analogy we have understood by the band diagram. Now the same energy you understood by the crystal structure. Is there any free electrons? All electrons are making the bond, and there is no thermal energy. Since there is no thermal energy, that means no free electrons are there. So if all are making the bond, no free electron is there, then can the electrons move? No, only free electrons can move. These electrons are bound, so they cannot move. So you can understand the analogy by the crystal structure as well, along with the band diagram as well. So in band diagram, if I had applied any electric field, everything we are talking, any potential at 0 Kelvin, we are just talking about 0 Kelvin. At 0 Kelvin, in the band diagram, you can see that conduction band is completely empty and valence band is completely filled. There are no free electrons. Electrons have no other part to move. So even if you apply the battery, there will not be any current flow. So at 0 Kelvin, your silicon crystal, your semiconductor, this silicon crystal is named as semiconductor. It is working as a perfect conductor. Sorry, as a perfect insulator. So all the theory, everything is written, but are you able to understand this point? So this silicon crystal at 0 Kelvin is working as a perfect insulator for us. But now what if I see it at the room's temperature? What if I see it at the room's temperature? But before that, let's see the theory that we have already written. So at absolute 0 Kelvin temperature, a silicon crystal behaves like a perfect insulator. The valence band is completely filled with electrons and the conduction band is completely empty. So there are no free electrons. If no external electric field is applied, the electrons remain bound and cannot move freely. Even if an external electric field is applied, no current can flow because the fully filled valence band cannot contribute to the conduction and the conduction band has no electrons. So conduction band is having no electrons, valence band is completely filled, so there cannot be any chance of current flow. Thus at 0 Kelvin, silicon cannot conduct the electricity under any condition. All good. But now what if we talk at the 300 Kelvin? So at 300 Kelvin, what will happen is that electrons will get some thermal energy at 300 Kelvin. And that thermal energy is 0.26 milli electron volt. So what will happen is that at room temperature, now these, let's understand by the crystal structure. First we are understanding by crystal structure. So what will happen is that at the room temperature, some of these bonds will break. This bond will break. So what will happen? Whatever the this electron was here, this electron will go into this gap and it will create a vacancy. It will create a vacancy here. Previously at this particular space there was an electron. Now what really happened is that this electron has went into this free space. You will not call it free space, I will call it gap. This electron has went into this gap. So this electron has become free electron now. And this vacancy is known as hole. So here, because of their temperature only, this is having some energy of 26 millivolt. Because of that temperature, this bond gets broken. Here we have made a vacancy and this electron has went into the gap. The same scenario with respect to your Venn diagram. So what will happen is that this electron will get enough energy to clear this band gap. This electron will get enough energy to clear this band gap and it will reach into the conduction band. So what will happen is that here there will be one vacancy and the electron would have reached here. Another bond can broke, another bond can break. So what will happen? Here there is an vacancy. This electron has already reached here and this electron can also reach here. So at room temperature, because of the thermal energy, what is the thermal energy? 26 milli electron volt. Because of the thermal energy, these electrons have broken these bonds, or in the band diagram what you will say, these electrons from the valence band, they have made transition in the conduction band. Now one very interesting doubt can come. If you are thinking very deeply, what doubt will come? That sir, you said that this was 1.17, this we are talking at 300 Kelvin, okay? And at 300 Kelvin, this is approximately 1.1 electron volt. The energy gap is 1.1 electron volt at 300 Kelvin. And sir, just 1 hour back you said that if the electron wants to make the transition from here to here, if the electron wants to make the transition from one energy level to another energy level, then it needs to cover this much energy, which is E2 minus E1. And for silicon, this energy is roughly 1.1 electron volt. For silicon, this energy is roughly 1.1 electron volt. But your electron is actually getting 26 milli electron volt only. What I am saying, my electron at the room temperature is getting only 26 milli electron volt energy. But it needs to cross 1.1 electron volt energy. It needs to cross this 1.1 electron volt energy. So how this 26 milli electron volt energy is enough to make the transition from valence band to conduction band? A very, very good point. But the answer cannot be given as of now. The answer will be given when we study Fermi direct distribution. So with respect to complete mathematics, I will give you the answer. As of now, in a crude way, what you can understand is that electron is getting 26 milli electron volt energy. But this energy is continuous. Are you able to understand this point? This energy is continuous. 26 milli electron volt, it will keep on getting the energy. Are you getting this point or not? What is the doubt? Did you understand the doubt? The doubt is that the energy gap is 1.1 electron volt. And sir, you have previously said that if the electron wants to make the transition from here to here, that means it needs to cross the 1.1 electron volt energy. but at the room's temperature you are getting 26 milli electron volt energy only. So this energy is actually continuous. At the room temperature, all the time it is getting this energy. 26 milli electron volt, 26, 26, 26, 26, 26. So it will keep on adding up and it will make the transition. In a crude way, you can remember in this manner. But the actual mathematics I will give you when we study Fermi direct distribution. So this doubt can come, which is a very, very good doubt, that at room's temperature, the thermal energy of an electron is about 26 millivolt, which is enough to make some electrons move freely and conduct electricity. That means which is enough to make the transition from valence band to conduction band. How it is possible? Because actually it should be 1.1 electron volt. So how it is possible? That we will understand when we study Fermi direct distribution. Fermi direct distribution. Okay, but as of now you just need to remember that somehow it makes the transition, but all the electrons will not make the transition. Are you able to understand this point? What I am saying is that, sir, here there are 4 bound electrons. Every silicon atom is having 4 bound electrons, no? So if there are n silicon atoms, so total 4 n bound electrons are there. So all the electrons will not go from conduction band to valence. All the electrons will not go from valence band to conduction band. Only a few electrons will go. Let's just say in this silicon crystal you are having 100 silicon atoms. What you are having? 100 silicon atoms. If 100 silicon atoms are there, that means 400 bound electrons are there, because each electron is having 4 bound electrons. So 4 bound electrons are there. Now if all the bonds are broken, then all 400 electrons will be free. But this doesn't happen. Only 2 to 3 bonds will be broken. So only 2 to 3 electrons you will get. Are you able to understand this point? 100 silicon atoms were there. These 100 silicon atoms are able to give you 2 to 3 electrons. Are you able to understand this point? 2 to 3 electrons means these free electrons. 2 to 3 free electrons. Electrons are there, like total electrons are 400. So 400 electrons are there. Out of these, only 2 to 3 are free. Is that okay for you? Okay. Yeah, so let me erase. So as of now, let me just conclude what we have studied. At 300 Kelvin, there is thermal energy present. Because of this thermal energy, what will happen is that these electrons will make transition from the valence band to conduction band. It will get enough energy to make the transition from valence band to conduction band. Okay, and by the crystal structure also you can see that bonds are broken. So this is a free electron that we have made, and this is the hole we have made. Another bond I can break. This bond I will break. So here I have created a vacancy. This vacancy is known as hole, and this is known as free electrons. So what is hole? Hole is nothing but a vacancy of the electron. Hole is nothing but the vacancy of the bound electron. Now what will happen? Look, because of the thermal energy as well, because of this thermal energy, this electron can move, right? Because it is having some energy. So if it is having energy, that means it can move. But they will move in the random direction. Some will move here, some will move here, some will move here. So their net motion will be 0. Because of the thermal energy, the electrons can move, but their net motion will be 0. So if I want the current, if I want a net motion, then what I have to do? I will have to apply a battery. Because if I apply the battery, then electrons will be bound to move in a certain direction. What that direction would be? Electrons will be moving in the opposite direction to the applied electric field. So when there was no electric field applied, this was the condition. At 300 Kelvin, no electric field applied. At this point, you are having free electrons, but still these free electrons cannot move. These free electrons can move because of the thermal energy, but they are moving in a random direction. To make them move in a certain direction, what you need to do? You need to apply a potential difference. So what I will do now, at the 300 Kelvin, I am having my silicon crystal. Now I am applying the battery. So in silicon crystal at 300 Kelvin, I am applying V0 potential. So what will happen? This will be positive, this will be negative. So this will be your electric field. And since this is the electric field, so electron will move in the opposite direction to the applied electric field. So this electron will move, and this electron will also move. So these two electrons are moving, and since they move, you will get some current. So this electron, this particular electron that I have made here, this particular electron is moving in this direction, and because of that you are getting this current. So this electron is moving in this direction, that's why you are getting one current. All good. Now there is another electron which can move. Which electron? Think about it. There is a vacancy of electron, no? Vacancy means this is there, that this vacancy is saying that I am ready to take electron. And this electron, what this electron will say? Okay, if you are ready to make the if you are ready to take the electron and I am having electric field, that means now I will move from here to here. Because this bond is not there, no? This vacancy, this particular vacancy is saying that I am ready to take the electron. So what this electron will say? That I will move here. What this electron will say? I will move here. Just as this electron has moved here, what will happen is that the vacancy will be created here. And just as this electron has moved here, then what will happen is that vacancy will be created here. Vacancy will be created here. Then this electron will say that I will move here. Then what will happen? Vacancy will be created here. Basically, electron from here to here it has moved, so vacancy will be created here. Now what this will say? This electron will say that I will move from here to here. Electrons are moving in the opposite direction to the applied electric field. Electric field is here, so electrons will move here. So this electron will move here. So where the vacancy will be created? This vacancy is created. Now this electron will move here. Then where the vacancy will be created? This vacancy will be created. So electrons are moving in this direction and this vacancy is moving in this direction. Are you able to understand this point? This vacancy is moving in this direction. There are two kinds of electron. One electron is the free electron. This was the free electron. And other electron was the bound electron. Both kind of electrons were moving. Free electrons were directly moving because of the electric field, they were moving in this direction. Now because of the vacancy, what really happened is that these vacancies were saying that I am ready to take the electron. So since there is applied electric field, the electron said that okay, since there is applied electric field, we can move now. And if you are ready to take the electrons, then we will move. So electrons moved. And if they moved, they created a vacancy, and that vacancy is known as hole. So what do you see here? The electrons are actually moving in the opposite direction to the electric field. It means that holes are actually moving in the direction of electric field. Kind of, can you say that holes are moving in the direction of electric field? Holes are not a particle. Particles are electron only. Holes are not a particle. But since the electrons are moving, it feels like that holes are also moving. The vacancy is also moving. But the vacancy is moving in the same direction. Like this was the free electron, right? Then what I will do is that this was the free electron. Now the bound electron which are there in the covalent bond, they also moved in this direction. Because of that, this hole moved in this direction. So if bound electrons are moving in this direction, where will be the current? The direction of current will be this. Here I am writing IP. And here I will write down IN. Or let's write down IE, and here I will write down IH. Now, how much current component are there? One current component is coming because of this free electron, and other component is coming because of this bound electron. Now, if I say that in a semiconductor, total current is 5 microampere. 2 microampere current is coming because of the electrons. So now the user will ask which electron, free electron or bound electron, right? If I say in a semiconductor 5 microampere current is flowing, in those 5 microampere, 2 microampere current is because of the electrons. Now which electron, free electron or bound electron? So again and again you will have to say that in this 5 microampere current, 2 microampere current is because of the free electron and 3 microampere current is because of the bound electron. To avoid that confusion, what the scientists did, they named this current, this particular current, they named this current as hole current. Because if bound electrons are moving, that means vacancy is also moving. No, that means holes are also moving. Are you able to understand this point? Hole is not a particle. Hole is nothing but a vacancy of electron. But it feels like that this vacancy is moving. So someone can say that this current is coming because of the movement of this vacancy. Although it is because of the movement of electron. But just for the sake of understanding, people can say that this current is coming because of the movement of holes. So one current component will be because of the electrons and one current component will be because of the holes. So whenever I say in the whole electronics from now onwards, whenever I say electrons, that means I am talking about free electron only. From now onwards, whenever I say electrons, that means I am talking about free electrons. And whenever I say hole, I am talking about the vacancy that is there in the covalent bond. The vacancy that is there in the covalent bond, that is the hole. And what is the free electron? Free electron that is present in the conduction band. And here also you can see that if I apply an electric field, these conduction band electrons will have enough space to move, and these valence band electrons will also have the space to move, because these are the vacancy here, no? So they can move towards this vacancy. This is also partially filled. This is also partially filled. If both are partially filled, that means both kind of electrons can move. They can move like this and they can also move like this. Right? Are you able to understand this point? So in the theory, what will be written? At 300 Kelvin, at room's temperature, in the silicon crystal, because of the thermal energy, you will get electron hole pair. Now what is this electron hole pair? Electron means free electrons. And what is hole? Hole is the vacancy of electron. If I apply a battery, if I apply a external electric field, if I apply this external electric field, the electrons will move opposite to the direction of a electric field. When I say electrons, that means the free electron. So free electron is moving in the opposite direction to the electric field, and the holes are moving in the same direction as the electric field. This is the direction of electric field, this is the direction of hole movement. So holes are moving like this. So there are two current component. One current component is coming because of the electrons, that means free electron, and one current component is coming because of the holes, that is vacancy of electrons, or you can say because of the movement of bound electrons. Is this point clear? Like a very, very good point. Usually people don't understand this particular point. Usually student gets confused there. But is that clear? So hole is there, the word hole is introduced just to make you understand the things in an easier manner. So if someone says that 5 microampere is the total current, 3 microampere current is because of the electrons, that means because of these electrons, these free electrons, and 2 microampere current is because of the holes, that means because of these vacancies. Is that clear to you? So complete theory is written. At 300 Kelvin, a silicon crystal gains enough thermal energy for some electrons to jump from the valence band into the conduction band. Each electron that moves up leaves an empty state in the valence band, which behaves like a positive charge carrier. Yeah. Why positive charge carrier? Like electrons are negative charge carrier. Hole I will call as positive charge carrier. Why is that so? Because in the presence of electric field, if there is a charge Q, it will get some force, right? It will feel some force. And if this charge is moving getting the force in the same direction as the electric field, if this charge is moving in the same direction as the electric field, what does that mean? That means this is a positive charge. So if electrons are the positive charge, then holes are like, if electrons are the negative charge, then holes are like the positive charge. Are you able to understand this point? If electrons are like the negative charge, then holes are like the positive charge, because they are moving in the same direction as the electric field. What is the direction of electric field? This is the direction of electric field. So holes are moving in the same direction as the electric field. That means they feel like as a positive charge, but actually they are not a particle. Holes are actually not a particle. They feel like a positively charged particle, right? So this is what is written. What is written? Each electron that moves up leaves behind the empty states in the valence band, which behaves like a positive charge carrier, called as hole. Called a hole. Thus, at room temperature, silicon have equal number of electrons in the conduction band and holes in the valence band, right? Equal number of electrons in the conduction band and equal number of holes in the valence band. You can directly see that whatever the number of electrons are going in the conduction band, the same number of holes are present in the valence band, no? Like if electrons are going, then only you will get the holes, no? Like if this electron goes here, if you get a free electron, that means you will surely get a hole. If you get a free electron, that means you will surely get a hole, right? So free electrons are present in the conduction band. Free electrons are present in the conduction band and holes are present in the valence band, right? If no external electric field is applied, the both electrons and hole will have a random motion, will move randomly because of the thermal energy. I told you, like because of the thermal, if there is energy, that means there will be velocity, but the velocity will be very random. They will move here and there. The velocity will be very random. If the velocity is random, that means there will be no net current flow. So even if you are having free electrons, even if you have space to move, still the movement is very random. Since the movement is random, that means there will be no current flow, right? When an electric field is applied, electrons drift opposite to the field and holes drift in the direction of the field, creating a small but definite current. The current will flow, but the value of that current would be low. Okay, the magnitude of that particular current will be low, but the current will flow. Okay, this is why at 300 Kelvin, intrinsic silicon acts as a weak conductor rather than a perfect insulator. So at 0 Kelvin, what we were getting? At 0 Kelvin, we were getting cannot conduct electricity, and here we were getting insulator. But at 300 Kelvin, we are getting a conductor, not a perfect conductor, not a very good conductor, a weak conductor. Like at least some current we are getting. Okay. Note, in semiconductor, the charge carriers are electrons and holes. What do you mean by charge carriers? So charge carriers are those particles which will help you in conducting the current. So who is helping you in conducting the current? This free electron and hole. So from now onwards, whenever I say free electron, whenever we refer to the electrons, we mean the free electrons present in the conduction band. So from now onwards, whenever I say free electrons, that means you need to think about the electrons that is present in the conduction band. And from now onwards, whenever I say holes, that means you need to think about the vacancy of electron that is present in the valence band. Okay, so this is the note we have written. Whenever we refer to electrons, we mean the free electrons present in the conduction band, and whenever we refer to holes, we mean the absence of electrons present in the valence band, which behaves like a positive charge carrier. And what do you mean by charge carriers? Charge carriers means those particles which will help you in conducting the current, which will help the current to flow. So who is helping the current to flow? These free electrons and these bound electrons. Bound electrons means holes only. Because if bound electrons moves, vacancy also moves. Vacancy moves, that means holes move. So here the charge carriers are electrons and holes. And here the number of charge carriers, number of electrons and number of holes both are equal. Okay. Is that clear to you? So that equal point I haven't written here, that will come later on. What I am saying, yeah, here it is written. There is equal number of electrons in the conduction band and holes in the valence band. So charge carriers are holes and electrons, and in this kind of a semiconductor, the number of electrons and the number of holes are same. Is that clear? Okay. What is electron? What is holes? Electrons are negatively charged particle moving in the conduction band, move opposite to the direction of electric field when field is applied. And what about the holes? Holes are the absence of electrons present in the valence band, behaves like a positively charged carrier, move in the same direction as the electric field. Now what is this? Energy increases upward in the Venn diagram, and here energy increases downward in the Venn diagram. What is the meaning of that? So I told you, for electrons, the energy will increase in the upward direction. Where I told you that? In the beginning of our slides only. Here. As you move upper, for the electrons, the energy will increase in the upward direction. The energy will increase in the upward direction. But now for the holes, electron energy increases in the upward direction, electron energy increases. Now just tell me one thing, electron and holes are like opposite charge only, no? Like electron is a negatively charged particle and hole is acting as a positively charged particle. What is the energy? Energy is Q into V. Forget about the V, just focus on Q. If it is negative, if Q is negative, then energy is increasing in the upward direction. So now if Q becomes positive, then what will happen? In the upward direction, energy will increase. Sorry, in the upward direction, energy will decrease. Are you able to understand what I am saying? And the definition of energy is Q into V. Forget about the V as of now, because V is the potential that we will apply, right? Now I am saying that if Q is negative, if we are talking about the electrons, then energy is increasing in the upward direction. So if Q becomes positive, then what will happen? Then energy will decrease in the upward direction, or you can see that energy will increase in the downward direction. If you go in the downward direction, the whole energy will increase. Just you need to understand that electron and holes are like opposite charge carriers. If one is positively charged carrier, then hole is like a negatively charged carrier. So if electron energy is increasing in the upward direction, then whole energy will increase in the downward direction. So this is the line that I have written. So let's just say I make some Venn diagram. This is the electron I am making. This is E2, this is E1. And this is E3, this is E4. And this is the hole I am making. Find the relation between E2 and E1. E2 will be greater than E1. The electron that is present on this energy level, the energy will be higher. But here, E4 will be greater than E3. This hole will be having more energy. But better than writing down, we should write down in this manner. This electron will have more energy. And this hole will have more energy. Because energy of holes increases in the downward direction, energy of electron increases in the upward direction. This point will be used somewhere, okay? In future, somewhere this point will be very, very crucial. So somewhere I will be using this point. As of now, are you able to understand this point? Hole is actually not a particle. This is just an analogy that will help us to understand a lot of diagrams, a lot of Venn diagram we will be understanding by this concept. Okay, so electron energy increases in the upward direction and hole energy increases in the downward direction. Is that point clear to you? Okay, so I need to take a break, then we will understand. Okay, I will explain this particular thing which you already know, and then I will take a break. Yeah, so the semiconductor that we studied just now, that is known as intrinsic semiconductor. So just now the semiconductor that we have studied, that is intrinsic semiconductor. What do you mean by intrinsic semiconductor? That means pure semiconductor with no impurities. That means everywhere silicon would be there, no? Everywhere silicon would be there. You see this, everywhere silicon. There is no other atom. So if everywhere silicon is there, that means it is intrinsic semiconductor. Okay, everywhere silicon is there, that means it is intrinsic semiconductor. In this intrinsic semiconductor, the number of free electron is always equals to the number of holes. That also I already told. Number of free electrons is always equals to the number of holes. Both combined are known as charge carriers. Okay, so we represent number of electrons by n and holes by p. When I say electrons, that means free electron only. So number of free electrons are n, number of holes are p. So for intrinsic semiconductor, n is equals to p is equals to ni. What is this ni? Ni is known as intrinsic carrier concentration. So in the examination, what will be given? In the silicon crystal, in intrinsic semiconductor, in intrinsic silicon semiconductor, the intrinsic carrier concentration is given as 10 to the power 10 centimeter, 10 to the power 10 per centimeter cube. That means in 1 centimeter cube volume, there are 10 to the power 10 electrons and 10 to the power 10 holes. in the examination, what will be given is that your intrinsic carrier concentration is 10 to the power 10 centimeter cube inverse. What does that mean? That means in 1 centimeter cube volume, there are 10 to the power 10 free electrons and 10 to the power 10 holes. And both will be same in case of intrinsic semiconductor, because electron hole pairs are generated in a pair, right? They are the pair. Why they are the pair? Because if one bond is broken, then what really happened? One hole we got. If one bond was broken, one hole we got. So electron and holes, number of electrons will always be equal to the number of holes in case of intrinsic semiconductor. Some other semiconductor we will study, there it may change. But in case of intrinsic semiconductor, N will be equal to P is equal to Ni. Is that okay for you? N is the number of electrons, P is the number of holes. Ni is known as intrinsic carrier concentration. And for silicon at room temperature under thermal equilibrium. What is this thermal equilibrium? As of now, you understand thermal equilibrium means constant temperature. At a constant temperature, that means you have at 300 Kelvin, you have reached the steady state. Now, no other electrons and holes are being generated. At 300 Kelvin, at a constant temperature, you have got the steady state. That means no other hole and electron hole pair are being generated. Electron hole pair is fixed. That means number of holes are also fixed, number of electrons are also fixed. That is equal to roughly around 10 to the power 10. It is not a fixed value, it can be varying, it can change. So it will be given in the questions. Sometimes it can be given as 1.5 into 10 to the power 10 as well. Okay, 1.5 into 10 to the power 10 as well. So it can vary according to the question. That means that in every cubic centimeter of pure silicon, about 10 to the power 10 electron hole pairs are naturally generated due to thermal energy. So because of the thermal energy, some bonds were broken and we got free electrons and the vacancy of free electrons and vacancy of electrons, that was known as hole. So we got electron hole pairs. Those are roughly around 1.5 into 10 to the power 10 for silicon crystal at room temperature under thermal equilibrium. Thermal equilibrium means the number of electron hole pairs are fixed now. Now it will not increase, it will not decrease. At thermal equilibrium, at steady state, 1.5 into 10 to the power 10 centimeter cube inverse, these number of free electrons and these number of holes you are having. Is this slide clear to you? Okay. So we have got some current now. In the semiconductor at 300 Kelvin, because we are having electron hole pair, we have got some current, right? But the current is actually very less. So although an intrinsic semiconductor can conduct electricity at room temperature, it's a very poor conductor. It's a very poor conductor. Its conductivity is too low to be useful in practical applications. So that's why we will not use intrinsic semiconductor. Now we will use extrinsic semiconductor. So there what we will do, we will dope the silicon crystal by adding small amount of trivalent atoms, which will create P type of semiconductor, and we will dope pentavalent atoms, which will create N type of semiconductor, and the conductivity will be improved. So as of now, we have built a silicon crystal. There we got to know that we are getting some conductivity, at least some conductivity we have got, and the conductivity is coming because of the free electrons and because of the holes. Conductivity is coming because of the free electrons and holes. If anyhow I increase the number of free electrons, if anyhow I increase the number of free electrons, and if I anyhow increase the number of holes, then my conductivity can increase. So for that, what we did, we started doping the pentavalent atoms and trivalent atoms. So what is this doping? How do we do it? Everything I will tell you, but after a break. Okay. So a semiconductor whose conductivity is improved by this way, that is known as extrinsic semiconductor. Extrinsic semiconductor. So as of now, we are going to study about extrinsic semiconductor. Now what is this pentavalent atom? What is this trivalent atom? That I will tell you after the break only. I need to take a break. I need to drink some water and then I will come back. We will study about pentavalent atom, trivalent atom, and from there we will make P-type semiconductor and N-type semiconductor. As of now, you should revise everything that we have currently studied. So it's been roughly around 2.5 hours. In this 2.5 hours, we have seen the basics of semiconductor. So let's meet after the break. Yeah, welcome back guys. So we were studying about intrinsic type of semiconductor. In that kind of semiconductor, we were having number of holes equals to number of electrons, and that is known as intrinsic carrier concentration. But we got to know that conductivity was pretty small. what is the expression of conductivity, all these things we will see later on in the lectures. Okay, but as of now you got to know that conductivity is very small. So now your target would be to increase the conductivity, you need more current. So for that what we are going to do, we are going to use extrinsic semiconductor. So what are extrinsic semiconductor? So in the intrinsic semiconductor only, so in intrinsic semiconductor what was the scenario? Silicon, silicon, silicon was there. So now in intrinsic semiconductor what we will do, we will dope pentavalent and trivalent atom. So either we will dope pentavalent atom or we will dope a trivalent atom. So what is this pentavalent and trivalent atom? So in your, do you remember your periodic table? So there were some group 3 element and there were some group 5 element. Why they were called group 3 element? Because in their outermost shell there are 3 electrons and in their outermost shell there are 5 electrons. They are having 3 electrons in their valence shell and they are having 5 electrons in their valence shell. So what all were the group 3 element? Boron, aluminium, gallium, indium and thallium, right? You can remember in your own way. How I remember? Bangan, alu, gajar in thela. Those who understand Hindi, they will understand. Bangan, alu, gajar in thela. You can remember on your own, right? Similarly here, nitrogen, phosphorus, arsenic, antimony and bismuth. These are the elements. New Zealand, Pakistan, Australia, sub BK. So just I am using Hindi language here, but whatever language you want to remember, in any way you want to remember, you can remember. Group 3 element and group 5 element. Okay. So in group 3 element, in the outermost shell you are having 3 electrons and in group 5 element, in the outermost shell, in the valence shell you are having 5 electrons. 3 electrons here, 5 electrons here. Now what we will do, we will create extrinsic semiconductor from these atoms. So how we will create it, that we are going to see. Okay, so basically we are going to study two kind of semiconductor, p-type semiconductor and n-type semiconductor. What is this p-type, what is this n-type, that we will study. So let's study about n-type semiconductor now. So this was our intrinsic semiconductor, right? Silicon, 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 everywhere silicon, silicon is there and all are making the covalent bond. Now what we will do, in this silicon we will insert some group 5 element. So I will be using phosphorus here. Okay, so what I am doing, I am inserting some phosphorus atoms. In place of silicon atom, what we will do, we will insert some phosphor atoms. So phosphorus is having 5 electrons in their outermost shell. Phosphorus is having 5 electrons in their outermost shell. So in place of silicon, if phosphorus is coming, silicon is gone, that means this electron is gone, this electron is gone, this electron is gone, this electron is gone. Now the phosphorus will come. Phosphorus will come. Phosphorus is having 5 electrons. So 4 electrons phosphorus will be using to make these bonds. So again 4 electrons are making the covalent bond. And this 1 electron will be nearly free. This electron is not completely free because phosphorus is having its own proton, right? It is having its nucleus. So this nucleus is imposing some force on these 5 electrons. Out of these 5 electrons, 4 electrons have made the bond. So they have made a stronger bond. They have made a covalent bond. Since they have made the covalent bond, that means they are not free. But this electron is also not completely free. This is approximately free. Or you can say this is nearly free. Or you can say this is loosely bound. They are strongly bound because they are making the covalent bond. But this is loosely bound. So the 5th electron is loosely bound. 4 are making the covalent bond. Now you let me know, if I talk about free electrons. So where are the free electrons? Free electrons will be staying in the conduction band, right? Free electrons will be staying in the conduction band, right? And bound electrons, which are the bound electrons I am talking about? These are the bound electrons, 1, 2, 3, 4. These are also bound electrons, 1, 2, 3, 4. All these are the bound electrons. So bound electrons always stay in the valence band, right? Free electrons stay in the conduction band. Now what about this electron? This electron is nearly free or it is about to be free. It is not completely free. This electron is loosely bound. So it is about to be free, right? So what should be its energy level? It should be near to EV or it should be near to EC. In EC, all free electrons are there. In EV, all bound electrons are there. This electron is nearly free, or you can say it is loosely bound. That means it is about to be free. If it gets some energy, if this electron gets some energy, it will be free. So it requires a very small amount of energy. That means this electron should be lying near to the conduction band. So near to the conduction band, I will make another energy level. That energy level will be known as donor energy level. What I am calling it? Donor energy level, because one electron is donated here. This phosphorus is donating one electron, and that electron is having energy near to the conduction band because it is about to be free, it is loosely bound. But only one phosphorus atom will not come into action, a lot of phosphorus atom will come into action. So this silicon will also be replaced by phosphorus, right? So 1, 2, 3, 4, 4 are making the bond, but one will be loosely bound. It is about to be free. So it will be here. So I am making some more electrons here, some more electrons I am making, right? So this is the scenario at 0 Kelvin. So at 0 Kelvin, you let me know. Now you will be saying that sir, you said that on one energy state only one electron would be there, but how you are making a lot of electrons here? Sir, few times back only you said that on one energy level only one electron would be there. Why you are making these many electrons? So this is not an energy state, this is an energy level. On one energy state one electron would be there, but on energy level, on one energy level a lot of electrons could be there, right? Do you remember 3p, 3s? So here I said that a lot of electrons are there, but just as this level got splitted into energy band, just as this level got splitted into energy band, at that time I said that on these energy states only one electrons will be there. So on the energy state only one electron can stay, but on energy level a lot of electrons can stay. So this is a donor energy level, okay? Donor energy level. So this is an important line, but these are the energy bands which are made from energy states. So on each energy state only one electron is there, but on donor energy level a lot of electron can stay. So this is the energy level, but these are the states. Difference is clear, right? Okay, everything should be crystal clear here, no doubt should be there. Now at 0 Kelvin, this electron is having any thermal energy? No. Is this electron is having any thermal energy? No. So no electrons are having any thermal energy. So at 0 Kelvin there are no free electrons. These are completely bound, right? And these are having no energy. So there is no free electron in the conduction band. Conduction band is completely empty. If conduction band is completely empty and valence band is completely filled, is there any chance of current to flow? No. So at 0 Kelvin, even if you apply the battery or even if you don't apply the battery, there is no chance of current to flow. Across this semiconductor, if I apply a battery, still the current will not flow. Why it will not flow? Because there is no free electrons in the conduction band, or there is no hole in the valence band, or you can say that conduction band is completely empty and valence band is completely free. So valence band is completely filled. So there is no free electrons who can move to conduct some current. So even if you apply an electric field, current will not flow. So this is what I have written. Okay. Okay, the theory will come later on, but as of now let's see at 300 Kelvin. So this is the scenario at 0 Kelvin, right? This is the scenario at 0 Kelvin, the same scenario we have made here. This is the scenario at 0 Kelvin. At 300 Kelvin, what will happen? This electron is just below the conduction band. That means this energy is very low. This gap is very low. And at room temperature, all of these electrons will be getting enough energy to reach into the conduction band. All these electrons will reach into the conduction band. Okay. All of these electrons will reach into the conduction band because they are just near the conduction band. So at room temperature, because of the thermal energy, they will reach into the conduction band. Along with that, some of these bonds will also break. This bond will also break. Let's just say this bond will break. So what it will do? It will create a hole and it will create an electron. This bond will also break. Let's just say this bond also breaks. So what it will do? It will create a hole. It will create an electron. That means this electron can also go to conduction band. So what it will do? The electron will reach here. The electron will reach here, but it will generate a vacancy. What may happen is that another energy level I need to make, another energy state I need to make. So what may happen is that this electron reaches here and it creates a vacancy. So electron hole pairs are also there. Now what do you see? In the conduction band, how many electrons do you see? 1, 2, 3, 4, 5, 6. 6 free electrons are there in the conduction band. How many holes do you see in the valence band? Only 2 holes are there in the valence band. So in the conduction band, 6 electrons are there and only 2 holes are there in the valence band. So electrons are more or holes are more? When I say electrons, that means I am meaning free electron only. So free electrons are more or holes are more? Which is more? Free electrons are more, right? These free electrons are more. And since free electrons are more, so in n-type semiconductor, majority charge carrier is electrons and minority charge carrier is holes. Okay, and that's why it is known as n-type semiconductor. Here what did you get to know is that majority charge carrier are electron and electrons are negatively charged. That's why n-type semiconductor. Okay, so in n-type semiconductor, what we did, previously we were having intrinsic type of semiconductor. Okay, there what we did, we doped some phosphorus atoms. So each phosphorus atom is having 5 electrons in its valence shell. 4 electrons are making bond, 1 electron is loosely bound. It is nearly free. It is not completely free, it is nearly free. That's why it will be lying in the donor energy level just below the conduction band. At 0 Kelvin temperature, none of the electron is getting enough energy to go from donor energy level to conduction band. So conduction band is completely empty and valence band is completely free. Sorry, valence band is completely filled. Even if you apply any electric field, there will not be any current at 0 Kelvin in n-type semiconductor. But at 300 Kelvin, what really happens is that because of the thermal energy, all the donor energy level electrons will reach into the conduction band. And some electrons from the valence band will also reach to the conduction band, creating a small vacancy which is known as hole. So in the valence band, you are having some holes and in the conduction band, you are having a lot of electrons. So majority charge carriers are electrons and minority charge carriers are holes. And now if I apply the battery, look here I have made only 6 states. More states would be there, no? So don't think that this conduction band is completely filled. No, nothing like that. More states are there. So now these electrons have enough space to move. Like this electron can also move now. This electron can also move. Along with that, these electrons can also move, right? Basically, the way I apply the battery, let's just say I apply the electric field in this direction. So where the electrons will move? Electrons will move in this direction. So this electron can move, this electron can move, this electron can move. Now what will happen is that this electron can also move. So this vacancy will move ahead. So this mechanism we have already seen. So basically now there are free electrons available. So if I apply the electric field, electrons will move in the opposite direction to the applied electric field. And if electrons are moving, that means there will be current flow. Along with the electrons, this vacancy is also moving. So that's why there will be current flow because of this vacancy as well. But that current will be very low. Why that current will be very low? Because number of holes are very low. Here number of holes you could see 1 and 2 only, but you can see electrons 1, 2, 3, 4. A lot of free electrons are there. So free electrons would be much more than the number of holes. That's why the majority current would be there because of the free electrons only, not because of the holes. Are you able to understand this point or not? Okay. So I hope you have understood. This complete theory has been written. So in n-type semiconductor is formed when a pure semiconductor like silicon is doped with pentavalent atom. It could be phosphorus, arsenic, antimony, it could be anything. These atoms will have 5 valence electrons, 4 of them will be making the covalent bond with the neighboring atoms and 5th electron will be left loosely bound. Okay, the word is written that is loosely bound, it is nearly free. This extra electron create a special energy state just below the conduction band known as donor energy level. Okay, so donor energy level, in this donor energy level a lot of electrons will be lying there. Okay, and because the energy gap between the donor level and the conduction band, this energy gap between the donor level and the conduction band, this energy gap I am talking about, this energy gap is very low. This energy gap is very low gap. Very low gap. And since this gap is very low, since what is written, because the energy gap between this donor level and the conduction band is very low, the electron can easily jump into the conduction band using the thermal energy. Okay, at 0 Kelvin it will not jump. At 0 Kelvin it will not jump, but just as it gets the thermal energy, it will jump. Thus, in n-type semiconductors, electrons are the majority charge carriers, while the holes are the minority charge carriers, right? Because number of electrons will be much more than the number of holes. Let me give you an example. Let's just say initially we were having 100 silicon atoms. Although the number will be very much larger, just for the understanding purpose I am doing it. So we were having 100 silicon atoms, like silicon, everywhere silicon was there. At room temperature, what will happen? All the silicon atom will be broken. What I mean to say is that all these electrons will go into the conduction band. No, only few bonds will be broken, right? I told you here only when we were studying intrinsic semiconductor. At that time also I told you that this energy gap is larger. This energy gap is large. So all the electrons will not be able to clear this energy gap. Only a few electrons will be able to clear this energy gap. So if I am having 100 atoms of silicon in the intrinsic semiconductor, I am talking about intrinsic, I am talking about pure semiconductor. In the pure semiconductor, I was having 100 silicon atoms. That means I was having 400 valence shell electrons. But out of these 400 valence shell electrons, only a few, let's just say only 10 electrons went from valence band to conduction band. So if 10 electrons is going from valence band to conduction band, that means 10 electrons you have got and 10 holes you have got at room's temperature. This is happening at room's temperature. Now what you have done? You have done the doping. You have done the doping. So 100 silicon atoms you were having. Now you have done the doping, that 50 phosphorus atoms you added. What you did? You added 50 phosphorus atoms. Now one phosphorus atom is giving you one loosely bound electron, right? One phosphorus atom is giving you one loosely bound electron. So 50 phosphorus atom will give you 50 loosely bound electrons. 50 loosely bound electrons. Now all the electrons will be lying just below the donor energy level. This is the energy level. So all the electrons are having the same energy, right? All these electrons, all these loosely bound electrons are having the same energy. And this is just below the conduction band. Now just as you go at the room's temperature, just as these electrons get the 300 Kelvin temperature, what they will do is that they will make a transition from conduction band to valence band. So what you did? You did the doping of 50 phosphorus atoms. These 50 phosphorus atoms will give you 50 electrons, loosely bound electrons. But at the room temperature, all the 50 electrons will be getting into the conduction band. Are you able to understand this point? So now you can see previously 10 electrons were there. Now 50 more electrons are there. So number of electrons have become very larger, and number of holes, previously it was 10 and now it did not get changed. It will change, but it will reduce only. What I am saying is that these 10 holes will be reducing. Why it will be reducing, we will understand later on. But as of now, you are able to understand that previously there were 10 electrons and now 50 more came into action. Because here all 50 are going in, but here all 400 are not making the electrons. Are you able to understand this point? At the room's temperature, all 400s are not making the electrons. Only out of these 400s, only 10 are making the electrons. But when you added the impurity, each atom is giving you one free electron, and that free electron at room's temperature is going into the conduction band. That free electron at room's temperature is going into the conduction band. So all 50 are ionized here. So 50 electrons because of the impurity and 10 electrons were already there. So total electrons will not be addition. Okay, there is some other law. That law we will study, but you can surely see that 50 and 10 number has become very larger, but number of holes are pretty low only. Okay, this is a very deep understanding that what is actually happening. Like people would be saying that, sir, okay, electrons are also going here. No, so holes can also be very large. But actual thing is that these electrons will not be broken. These covalent bond electrons will be very less. These covalent bond electron holes, this pair will be very less, but these electrons will be very much more. Are you able to understand this point? So that's why holes are minority and electrons are majority in case of N-type semiconductor. Is that clear to you? Now more things. They are known as donor atoms. What they are known as? Donor atom. Donor atom. So I will show it by Nd. Okay, donor atom, Nd. Donor atom, Nd. Okay. Now at 300 Kelvin, what will happen is that thermal energy excites the electron. Yeah. So at 0 Kelvin, I forgot to read. At 0 Kelvin, at absolute 0 Kelvin temperature, all electrons, including the donor electrons, remain tightly bound, since there is no thermal energy to excite them into conduction band. Hence, no free electrons are available for the conduction. With or without electric field, the N-type semiconductor will behave like an insulator at 0 Kelvin. But at 300 Kelvin, at room's temperature, without electric field, we are not applying the electric field as of now. Okay, without electric field. So at 300 Kelvin, at room's temperature, without electric field, what will happen is that thermal energy excites the donor electrons from the donor level into the conduction band. This will give a large number of free electrons compared to the intrinsic semiconductor. In addition, some electron from the valence band will also get excited to the conduction band. Some electron from the valence band will also get excited to the conduction band. leaving behind holes in the valence band. However, since no external electric field is applied, these electrons will be moving randomly, hence there is no net current. Because if there is no electric field, that means there cannot be any current. If it is a simple piece of silicon, and you are not applying any electric field, there will not be any current, because electrons can move, right? Here they are having free space, they can move, but they are moving randomly. But if I apply the electric field, they will move in a certain direction, and if they are moving in the certain direction, it will give us some current. Okay, so movement in certain direction is important. But as of now, without electric field, this is the condition, without electric field, they are moving randomly. Okay, and by default you will be considering at room temperature only. Let us say some question is coming there, they did not mention any temperature. They are saying that there was a intrinsic silicon semiconductor we were having, and then we doped some donor atoms in it. So donor atoms we used 10 to the power 10. Let's just say they will say that we have done the doping of 10 to the power 10 atoms per centimeter cube. So in 1 centimeter cube volume, we have doped 10 to the power 10 atoms. So at which temperature this is happening? At room temperature it is happening. So you will, by default, you will assume that all 10 to the power 10 atoms will give them free electrons. So all these 10 to the power 10 electrons are giving them free electrons. By default, you will be there at the room temperature only. You will not say, sir, there is no temperature, that means these are of no use. They will not conduct the current, because you will say that, sir, at 0 Kelvin they are of no use because they are not reaching at the conduction band. But by default you will always be at the room temperature only, at 300 Kelvin only. Okay, so by default you will say that all of them are ionized, all of them have gone from donor level to the conduction band. Okay, now how would I represent n-type semiconductor? So this is my semiconductor, this is my semiconductor. Okay, this is my semiconductor I am having. Now what phosphorus atom is doing? It was having 5 electrons, right? 4 electrons are making bond, 4 electrons are making bond, and it is donating some electron. 4 are making the bond and 1 electron it is donating. So it is the donor atom, and once you become the donor, you become positive, right? If I give my electron to someone else, what I will become? I will become positive, no? Because I am giving something. That means I will be getting the interest, right? If I am giving you 10 rupees today, tomorrow I can get a 1% interest. So I can get 10.1 rupees next day. 1% interest. Just a joke, okay? Basically, you will become positive, no, if you donate something. So phosphorus will become positive. How I am donating it? By the donor atom. So donor atom are having 4 electrons. Sorry, donor atom are having 5 electrons. 4 are making the bond. 4 are making the bond, and 1 is they are donating. 1 electron they are donating. So donor atom will become Nd positive. So on the donor atom, positive charge will come. Along with the positive charge, they are donating an electron as well. So this is how I will show my n-type semiconductor. Donor atom is becoming positively charged. Along with the positive charge, they are having 1 electron as well. Donor atom is becoming positively charged. Along with that, they are having an electron as well. Positively charged electron, positively charged electron. This has become positively charged. Along with that, they are donating 1 electron as well, no? So this electron I am making. Positively charged electron, 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 positively charged electron. So this, because of the phosphorus I have made. Some electron hole pair will also be generated, no? Electron hole. So some electron hole pair will also be generated. So minority hole concentration will also be there. Minority hole concentration will also be there, and because of these holes, some free electrons would have also been made. So usually in many of the diagram you would see that they will not make these. They will only show these electrons. That's it. The electrons which are coming because of the donor atom. But you can also show that there will be minority holes as well. When we will be studying p-n junction, at that time I will make these minority holes as well. Okay, and then because of these holes, some electrons will also be there. So you don't need to make these electrons because a lot of electrons you have already made. Just I have made some small holes as well. What these holes are saying? These holes are saying that minority holes are also there. electrons and minority holes are also there. So this is how I will be representing my n-type semiconductor. Is that clear to you? In some diagram, if I forget to make this, don't be confused. Okay, if I am forgetting to draw the minority charge carriers, then it is fine. In a lot of diagram you would not see minority charge carriers, but majority charge carriers, this is how I will be making. Now you just let me know, this particular semiconductor, this particular material, is it positively charged, it is negatively charged, or it is neutral? This particular semiconductor material, look at this diagram, look at this diagram. This diagram and this diagram both are same, right? This diagram, this is the semiconductor only, and this is the same semiconductor. So look at the diagram and let me know, is it positively charged, negatively charged, or neutral? When it is donating some electron, what it is becoming? Positively charged. When it is donating some electron, what it is becoming? Positively charged. This positive charge has been neutralized by this negative charge. This positive charge has been neutralized by this negative charge. This negative charge has been neutralized by this hole. This negative charge has been neutralized by this hole. So this semiconductor is electrically neutral. Like when I represent Nd as Nd plus, they will say that okay, n-type semiconductor is positively charged. No, it is not positively charged. It is electrically neutral. Because if it is becoming positively charged, that means it is giving some electron as well. So there is electron also present, there is positive charge also present. So positive, negative, they will cancel out each other. It is electrically neutral. That's why they will not show these holes. They will only show this particular thing, and then they will tell that positive electron, positive electron, positive electron, positive electron, positive electron. So everything is being neutralized. Although I will show holes here as well, because they are the minority charge carriers. Is that clear to you or not? So this n-type semiconductor is electrically neutral. So this is what I have written. Even after doping, the semiconductor as a whole remains electrically neutral. This is because every donor atom, when it donates an electron, it becomes a fixed positive ion, balancing the charge of the free electron when it is released. Okay, is that clear to you? Right. Now, across this semiconductor, across this n-type semiconductor, what I am going to do, I am going to apply the electric field. First, what we studied, absolute 0 Kelvin temperature with and without electric field. Then we studied 300 Kelvin temperature without electric field. Now we are going to study 300 Kelvin temperature with electric field. Okay, and even if the temperature is not mentioned, by default you will take 300 Kelvin temperature only. Is that okay for you? So there is this semiconductor, across this I am applying a V0 battery. Okay, so what will happen? Because of this V0 battery, here there will be positive charge, here there will be negative charge. Because of that, there will be an electric field. This electric field will be E. I am calling it E external because it is coming because of the external source. This battery you applied. So externally you are applying the battery, right? So that's why it is known as external field. So I am applying an external electric field. Electrons will move opposite to the electric field. So electrons will move here. If electrons are moving here, that means electrons are moving in this direction. And since they are moving in this direction, so current of electrons will be in this direction. So I am representing current because of the electrons. What about the hole? This is the minority charge carrier. Hole will move in the direction of the electric field. Holes will move in the direction of the electric field. Holes will move in the direction of the electric field. So these are the holes which will be moving in the direction of the electric field. And since they are moving in the direction of the electric field, what will be the direction of the current? Direction of the current will be in the same direction as the hole. So this will be the direction of the current, right? I told you hole behaves like a positively charged particle and electrons behave like a negatively charged particle. Since they are the negatively charged particle, so they will move in the opposite direction to the electric field, right? And since they are moving in the opposite direction to the electric field, then the current will be in the direction of the electric field. What about the holes? Holes will move in the same direction of the electric field. And since they are moving in the same direction of the electric field, the current, basically if holes are moving in the same direction of the electric field, what does that mean? That means electrons are moving opposite, right? Because here only I told you, this hole is moving here. What does that mean? This electron is actually moving here. So this current is coming because of the movement of electron only, not because of the movement of hole. Just for the understanding purpose, we are saying that holes are moving, but actually electrons are moving. And since these electrons are moving here, holes are moving here, so the direction of current would be in this direction only, right? So from now onwards, I will just say that holes will move in the direction of the electric field and the current will also be in the same direction of the movement of hole. Okay. So in your mind, what you will think, okay, holes are moving, that means electrons are moving. Which electrons are moving? Covalent bond electrons are moving. And since they are moving here, so the direction of electric field, so direction of current would be in the opposite direction, or you can say in the same direction of the hole movement, or in the opposite direction of the covalent electrons movement, right? So total current, I total would be electron current plus hole current, right? But you know one thing, what do you know? That since number of electrons are very much larger than the number of holes, right? Number of electrons are very much larger than the number of holes. So this IN component will be very larger than the IP component. So this I total will approximately be IN. Basically, in the current, majority contribution is of electrons only, because number of electrons are much more larger than the number of holes. Is that clear to you? So this theory is written. When an external electric field is applied, free electrons will drift opposite to the field. This is known as drift current. Okay, what this is known as drift current, because electrons are drifting because of the electric field. Electrons are drifting or holes are drifting because of the electric field. Although we will write down the definition, don't worry about that. This is the drift current. There will be some diffusion current as well. So definition and everything we will write down. Don't worry about that. Just I am telling that if electrons are drifting, if electrons are moving because of the electric field, that's why it is known as drift current. So drift word is coming, that means electric field is there. If the drift word is coming, that means electric field is there. There will be another mechanism because of that electrons can move, and that would be diffusion. So that we will study later on. But as of now, electrons are moving because of the electric field. So if electric field is there, that means drift word would come into action. Okay. Yeah. So in N-type semiconductor, electrons are the majority charge carriers. So the current is mainly due to their motion, making the material as a good conductor. Holes are few in numbers, contribute very little to the contributes very little to the current. Okay. So what did you understand here is that in the intrinsic semiconductor we were having lesser current, but in the extrinsic semiconductor what we have done is that we have increased the number of charge carriers. The number of charge carriers have been increased. Previously 10 electrons were there and 10 holes were there. I am speaking thus. In English we call it 10. So previously 10 electrons were there and 10 holes were there. What we did? We introduced donor atoms. 50 donor atoms. All 50 donor atoms will give you 50 electrons, right? So total number would be somewhat different. That formula we will see later on in the next lecture only. We will see that formula, but you could see that from 10 to directly 50. Like at least 50 it would be. It would be more than 50 only. At least 50 electrons would surely be there. Are you able to understand this point? So we have increased the number of charge carriers. Previously number of charge carriers were 10 and 10. You can collectively you can call 20 charge carriers were there, but now already 50 electrons are added. Okay. Yeah, so we have increased the conductivity, so now it is working as a good conductor. So previously here we saw that in the intrinsic semiconductor it was not a good conductor, it was a very poor conductor. But now what we have done is that we have made a good conductor which is conducting some good current. Is that clear to you? Okay. So in the same manner that we have studied N-type semiconductor, in the same manner we need to study P-type semiconductor, and everything regarding the P-type semiconductor you would be able to tell on your own. So in P-type semiconductor, what do you think, which kind of atoms I will dope? Doping means just including the atoms. Doping is a separate process. Like if you want to study the process of doping, that's how I am actually doing it. Like on the silicon crystal, how I am actually introducing phosphorus here. So that process is studied in IC technology that has been removed from the syllabus. So we are not going to study it. As of now, you will just study that doping means some atom is coming and replacing one particular atom. That's it. This is what you will understand. But doping is a separate process that you don't need to study. So now, what do you think? What kind of atom I will be doping here? I will be doping group 3 atoms: boron, aluminium, gallium, indium, helium. So I will dope boron, or you can dope aluminum as well. So let's dope boron here. Okay. So in the outermost orbit or in the valence shell, how many electrons boron is having? Only 3 electrons. So let's just say in this place of a silicon, boron is coming. So these 4 electrons are gone. Who is coming? Boron is coming. So boron is saying that I am having only 3 electrons. So all these 3 electrons will make the covalent bond. What will happen here? Here vacancy will be there. Are you able to understand this point? Here vacancy will be there, no? Right? Another boron atom will come. Let's just say it is coming here. So what boron atom will say? Boron atom will say that, sir, I can make 3 bonds because I am having 3 electrons, but one vacancy I will have. Now this vacancy is ready to take electrons. This vacancy is not coming because of the temperature. This vacancy is coming at 0 Kelvin only. This is not electron hole pair. Like this electron is gone and then electron hole pair we are getting. No. This vacancy is coming because of the boron atom. So this vacancy is ready to take this electron. Are you able to understand this point? So what do you think where this holes will be there? Like what will be the energy level of these holes? Here are our bound electrons, right? Here are our bound electrons. This electron I am representing here. This electron I am representing here. This electron I am representing here. So these are our bound electrons. This hole is ready to take these bound electrons. That means this hole should be near to these electrons only, you know. Like if you give just room temperature, what will happen is that this will move. As of now they are bound because they are not getting any temperature. Just as they get the temperature, they will say that okay, near to me only I am having some vacancy, I can move. Or this electron will say that I will move. So at the room's temperature, they will move. That means they are ready to take the electron. This hole is ready to take the electron. That means it will be near to the valence band. Say yes or no. So just above the valence band, you will be having acceptor energy level, because here what you are having holes. What you are having holes. So this is your acceptor energy level. Let me make more here. Similarly, in the conduction band as well, there will be a lot of states, but I am making only few. So this will be your acceptor energy level, which is made just near to the valence band. Why near to the valence band? Because this vacancy is saying that yes, I am ready to take the electron. But at 0 Kelvin will it happen? No, because at 0 Kelvin they cannot move. So this hole will also remain as it is. This vacancy will remain as it is. These electrons will remain as it is, and this will remain empty only. So what do you think? At 0 Kelvin, will there be any current? No, because conduction band is completely empty and valence band is completely free. Sorry, valence band is completely filled. Why? I don't know why I again and again say free. I want to say filled. Okay. So conduction band is completely empty and valence band is completely filled. And since they are completely empty and completely filled, there is no chance of the current, even if you apply an external electric field. So at 0 Kelvin, even if I apply an external electric field, it will not conduct any current. But at room's temperature, they will get enough thermal energy to go from here to here, right? So this is what we are going to see. At 300 Kelvin, what will happen is that these are the holes. These are not clear. I will make it clear. So these are the holes you are having. And these are the valence band electrons. These are the valence band electrons. Okay. Yeah. So they will get enough energy to recombine here. So this electron will go here. So what will happen? You can say that what you can say, this electron, or from here you can say that this electron will go here. So what will happen? Another vacancy is made here and this electron has reached here. Previously this electron reached here, now this electron reached here, right? Now what will happen is that this electron has reached here, now this electron will reach here. So it will create a vacancy and this will reach here again. So in that manner, and some electron hole pair will also be generated, because at that temperature some electrons will get enough energy to reach here as well. So some electron hole pair will also be generated. So here another hole is generated and another electron is generated. What I mean to say is that some these covalent bond will also break. No, this bond will also break, electron hole, right? This bond will also break, hole and electron, right? So let's just break one more bond. Right. Now what do you see? There are a lot of vacancy in the valence band. There are a lot of holes in the valence band. And in the conduction band there are very fewer free electrons. So these are the free electrons. What do you see here? Free electrons are 1 and 2. But how many vacancies are there? 1, 2, 3, 4. Here I did not replace the vacancy. What I mean to say is that someone would be saying that, sir, from here electrons are going into the from here electrons are going, that's why they are making this hole, right? So what you would show here, that this electron would go here and it will create a hole. So number of hole will remain same only. What I mean to say is that, sir, in diagram why you did not show that electron will go from here to here? Electron will go from this place to the hole. So what will happen is that here vacancy will be made and here this will be filled. So basically vacancy will be there. Vacancy will only be 1. Are you able to understand this point? So that's why I did not show it in this manner. That because of the boron atom there was one vacancy, that vacancy is remaining there only. Just for your understanding purpose, what is happening is that from the valence, these valence shell electrons are getting enough energy to fill the vacancy. These valence shell electrons are getting enough energy to fill this vacancy. Like these electrons will get the energy, it will fill this vacancy. These electrons will also get the energy, it will fill this vacancy, and then they will end up making holes. So all the vacancies that was there in the acceptor energy level, all the vacancies will be filled. So there were how many vacancies? 6 vacancies were there, and because of these 6 vacancies, 6 holes were made, and 2 holes are made because of these covalent bond being broken, right? So 2 holes are made because covalent bonds were broken. So 2 holes and 2 electrons were made because covalent bonds were broken, and rest of the holes are becoming because of the boron atom. So every boron atom will give you 1 hole. Every boron atom will give you 1 hole, and this hole will be taking any kind of electron. If you apply any electric field, with respect to the electric field, electrons will move. Covalent bond electrons can also move. This hole is ready to take the electrons, and since the electrons are moving, that means you will get some current for sure, right? So you can see that in valence band there are a lot of holes. Since there are a lot of holes in the valence band, that means yes, there are vacancy. If vacancies are available, what does that mean? Electrons can move. In the conduction band as well, there are some electrons, but they are very few electrons. So majority of the current will be coming because of the valence band holes only, not because of the electrons. So here who will be the majority charge carriers? Holes will be the majority charge carriers. And who will be the minority charge carriers? Electrons will be the minority charge carriers. Is that clear to you? And since holes are the majority charge carriers and holes are positively charged, that's why it is known as p-type semiconductor. Is that clear to you or not? Well and good. Did you understand this point? So at 0 Kelvin, with or without electric field, it will always work as insulator. At 300 Kelvin, yes, we are having free electrons, we are having holes as well. But since there is no electric field, they will be moving randomly, and since they are moving randomly, the total current would be 0. But just as I apply the electric field, what will happen is that this electron will come here. That means holes will be moving in the direction of the electric field, and electrons will be moving in the opposite direction to the applied electric field. And because of this net motion, there will be some current, and that current would be good enough to call it a good conductor, right? So all these theories have been written. A p-type semiconductor is formed when a pure semiconductor like silicon is doped with trivalent atom such as boron, aluminum, gallium. These atoms have 3 valence electron which form covalent bond with the neighboring silicon atoms. However, one bond remains incomplete, creating a hole which acts as a positive charge carrier. Hole will act as a positive charge carrier only. This creates a special energy state just above the valence band because these holes are ready to take the electrons, called the acceptor energy level. This energy gap between the acceptor level and the valence band is very small, so electrons from the valence band can easily jump into the acceptor level, leaving behind some holes in the valence band. Thus, in the p-type semiconductors, holes are the majority charge carriers and electrons are the minority charge carriers. Okay, and from where these electrons are coming? These electrons are coming because of the thermal excitation from the valence band to the conduction band. From the valence band to the conduction band, or you can understand by the crystal structure as well. By both of the analogies I am explaining you, by the crystal structure along with that band diagram as well, right? At 0 Kelvin temperature, there is no thermal energy present, so holes does not get like holes will be existing there, but they are not filled with the valence shell electrons, right? Valence band electrons. Basically, conduction band is completely empty at 0 Kelvin and valence band is completely filled. That's why there will be no current. This is what has been written here. No thermal energy is available. Holes do not exist because electrons cannot jump to the acceptor level. Holes do not exist where it doesn't exist. Holes do not exist in the valence band. Okay, they are saying that holes do not exist in valence band. In valence band or in the crystal structure as well. No, like here holes are not existing. They are ready to take the electrons, but this electron is not moving. No, this hole is ready to take the electron. This hole is ready to take the electron, but this electron will not move because there is no thermal energy, right? So when they are saying that no holes exist, when they are saying that no hole exists, that means they are talking about valence band and conduction band, not about this acceptor energy level. In acceptor energy level, there are holes, but they will not contribute in the current, right? Current contribution will be done because of this band or because of this band. Are you able to understand this point? The valence band is completely filled, so no conduction occurs. With or without electric field, the material will behave like an insulator. But at 300 Kelvin, what will happen is that thermal energy will excite electrons from the valence band to the acceptor level, creating holes in the valence band. Some electrons will also get thermally excited from the conduction band, from valence band to the conduction band. So some minority electrons will also be there and majority holes will also be there. Without an electric field, these motions will be very random, right? If you are not applying the electric field, then holes and electrons will be moving in the random direction. Since they are moving in the random direction, the net motion will be 0, and since the net motion is 0, the net current will also be 0, right? But just as I will apply the electric field, the current will flow. But before that, we will see the representation of a p-type semiconductor. So what do you think, what kind of representation would be there? Boron was having 3 electrons. What it will do? What boron is doing? It is taking 1 electron. So if it is taking some electron, that means it will be negative. If I am taking 10 rupees from you, tomorrow if I return the money, I will have to return you 10.1 rupee because of the interest. That means I am going into the loss. I have lost 0.1 rupee. So that means I am negative. So I will be negative. So if I am taking something, if the boron is taking some money, that means it will be negative. Here they were called as donor atom, right? Here I wrote donor atom. So here they are known as acceptor atom. Boron is a acceptor atom. Na. So in place of boron, what I am writing? Na I am writing. So Na is having 3 valence shell electrons and 1 vacancy it is having, which is ready to take the electron, That's why they will be negatively charged. So they are negatively charged, but they are giving you a hole as well. They are negatively charged, but they are giving you a hole as well. Negatively charged, giving you a hole. Negatively charged, giving you a hole. Not electron, hole. Negatively charged, giving you a hole. Negatively charged, giving you a hole. They are negatively charged, giving you a hole. Negatively charged, giving you a hole. Negatively charged, giving you a hole. Along with that, there will be some conduction band free electrons as well. So minority free electrons also I can make. Even if it is not made, then also you should not be getting confused. Minority charge carriers, they will not make some time. Okay, but in PN junction, I will surely make the minority charge carriers as well, right? So what do you think? It is electrically neutral or not? Yes, it is electrically neutral because boron is negatively charged, acceptor atom is negatively charged, but it is giving you a hole as well, and hole is positively charged. So here negative, positive, negative, positive, negative, positive, everything will cancel out, and electrically it is neutral. So it is neither positively charged, it is nor negatively charged, it is electrically neutral. Everything is electrically neutral. Every material you see, this is electrically neutral. Electrically neutral. If there was charge on it, then it will not be at the equilibrium. Like it would be continuously changing. Basically, there is no charge on anything. No, there is no charge on this mobile. There is no charge anywhere. Right? So every material is electrically neutral. So this is also a material only. No, this is a p-type semiconductor. This is also electrically neutral only. And from here as well, you can see that they are taking the electron. Since they are taking the electron, they are giving you a hole as well. So hole is a positive charge particle, and since they are taking the electron, that means they will be negatively charged. They will become a negatively charged ion. So what is this? This is a ion. This is like a ion. Na minus. This has become an ion, right? Negative ion, and this is the particle. I hope you understand the meaning between ion and particle. Ion does not conduct the current, but particle will conduct the current. This ion is not helpful in conducting the current. This boron is not conducting the current. This hole is conducting the current. Electrons are conducting the current. Here, electrons are conducting the current. This positive charge is not conducting the current. So this is also an ion. Are you able to understand this point? Okay. And at room temperature, here I said that all the vacancies are filled. So by default, we will consider that all the vacancies will be filled. But it might happen that in some questions it will be given that only 60% of the vacancies are filled, 70% of the vacancies are filled. What may happen is that, let's just say I am saying that I am doping 50 acceptor atom. What I am doing? I am doping 50 acceptor atoms. So 50 acceptor atoms should give me 50 holes. But they will say that ionization is only 70%. Ionization is 70%. What does that mean? That means only 70% of the holes are filled with the electrons. That means only 70% of the holes will be made. So you were expecting 50 holes, but 70% of 50, 35 holes only you will get. But if nothing is mentioned, you will assume 100% ionization. But if it is mentioned that 70% ionization is done, that means only 70% of the 50 holes you will be getting. That means 35 holes you will be getting in the valence cell, in the valence band. Okay. Similar thing can happen with this donor energy level as well. They will say that 50% of the donor atoms are ionized. 50% of the donor atoms are ionized. What does that mean? That only 50% of these electrons have reached to the conduction band. Rest 50% did not reach the conduction band because temperature was not enough. Anything can happen. Rest 50% were lying here only. They did not reach the conduction band, and if they are not reaching the conduction band, that means they are not contributing in the current. Current will be contributed only by this guy and this guy. Nothing in between. This guy is not contributing in the current. Which guy? This guy is not contributing in the current. If your electron is there in the conduction band, and if your holes are there in the valence band, then only they only will contribute in the current. Nothing else will contribute in the current. Electrons in the conduction band, holes in the valence band. That's it. So whenever I say conduction band, your mind should be going towards electrons. Electrons means free electron. Whenever I say valence band, your mind should be going towards holes. Right? Holes means vacancy of electrons. Is that okay for you? Right? So now what we are going to do, we are going to apply an electric field. So even after doping, the semiconductor remains electrically neutral because each trivalent atom that accepts an electron becomes a fixed negative ion, balancing the positive charge of the hole. Right? Negative ion balancing the positive charge of the hole. So this is electrically neutral. If I apply external electric field, what will happen? Here I should make a minority electron as well. So if I am applying the external electric field, or you can say if I am applying a battery V naught. So from here positive, this will be the positive side, this will be the negative side. So there will be an electric field that will be developed from positive to negative. So this will be your external electric field, right? Holes will be moving in the same direction of the electric field. Holes will be moving in the same direction of the electric field. So current will be this. And electrons will be moving in the opposite direction to the electric field. electrons will be moving in the opposite direction to the electric field. And since electrons are moving in this direction, so current will be there in this direction. So your total current would be IP plus IM. But you know that number of holes are very much greater than number of electrons. That's why IP component will be very greater than IN component. So from here, the total current would nearly be equals to the whole current only. Is that clear to you? Okay. So this line only will be written here. When an external electric field is applied, holes drift in the same direction as the applied field and electrons drift opposite to the applied electric field. Since holes are the majority charge carriers, the current is mainly due to their motion only. Electrons are few in number and contribute very little to the current. The semiconductor now conducts electricity efficiently compared to the intrinsic material. Okay. So now here also this has become a very good conductor, right? Now conducts electricity efficiently. So who is having better conductivity, intrinsic semiconductor or p-type semiconductor? So p-type semiconductor is having better conductivity. And if I compare between p-type and n-type, who is having better conductivity? So n-type is having better conductivity. Why so? That we will study in the next lecture. Okay. Look, intrinsic, extrinsic, who is better in terms of conductivity? Extrinsic is better. That's why we are making extrinsic. No, first we study intrinsic. In intrinsic we go to know that it is not enough. That's why we are studying extrinsic. So in extrinsic we studied two types, n-type and p-type. In n-type, majority charge carriers are free electrons, and in p-type, majority charge carriers are holes. In n-type and p-type, who is having better conductivity? N-type is having better conductivity. Why so? That we will study in the next lecture. Okay. But yeah, as of now, we have just seen the working, no formula, nothing. Only the pure concept we have seen, that how we are getting better conductivity. Formula and everything will come in the next lecture. A lot of questions will also come in the next lecture, and everything you will be able to solve. But in EDC, this is the beauty of EDC, that first you need to focus on theory, that we will see, then we will see problems and formula, and we will build up our problem solving skills. So in EDC, whenever you read any question, not in EDC only, in any subject I will tell you, whenever you read any question, it is not only important to solve the problem. Surely solving the problem is important, but when you read the question, each term, what each term is representing, what is the meaning of each term, you should know that. If you don't know the meaning of each term, still you are able to solve the problem, that means you are not actually learning. So I always say that whenever you are solving the PYQ, you read the question completely, line by line, and the meaning of each line, each word should be clear. And if it is clear, then you are saying that yes, I am going on the right path. As I say in EDC, like statement will be very large, but what student will do? They will do that, okay sir, this value is given, this value is given, this value is given, this formula I will apply, solve the question. This is the wrong way of solving the problems of EDC. 8 out of 10 questions you will get correctly. If you solve the problem in this manner, your efficiency will be 80%, and if you do the minor mistake, then your efficiency will go down to 50%. So your efficiency will be 50%. Now if you need to increase your efficiency from 50 to 80%, then you need to study the theory as well. Without studying all this theory, I could have directly started from the formula, and I would pick the PYQs, you would be able to solve it as well. But there is an importance of theory if you want to solve 100% of the questions. 20% minor mistake would be there, we cannot help it. Even if I know the 100% of the paper, I will get 80 marks only. That I know. About myself I am telling. I don't know about you. If I know 100% of the paper, I will get 80 marks only. Okay. So that I am telling about myself. So similarly, it would happen with a lot of students. But if you want to maintain that 80% of the efficiency, concepts are also important. Okay. Now we will see some definitions, some important points. Basically, now we will build up our formula. So from here to the next lecture, the same thing will happen. From here to the next lecture, the same thing will happen, that we will build up some formula and these kind of things. Like in this lecture, again and again I was using electric field. So what is this electric field intensity? How it is related to this voltage? So that we are going to see. Then we will see some types, like some basic thing we are going to see. As of now, what we have built up, sir, we started with semiconductor. Why semiconductors are important? How a particular material is made from atoms. In atoms, there is nucleus, electrons. Then we saw the energy splitting, and then we go to know that how energy bands are made. Now energy bands are made, then we go to know that we are having conduction band and valence band and the conduction band. Then we studied about intrinsic type of semiconductor. There everything was covered with silicon only. Everywhere silicon was there, covalent bonds were there. Since those covalent bonds were there, they were not breaking up at 0 Kelvin temperature. So we are not having any free electrons. So conduction band is completely empty and valence band is completely filled. So there is no current even if you apply the electric field. Then at room temperature what happens is that because of the thermal energy, some electrons from the valence band are going to the conduction band. So we are getting some vacancy there. Along with that we are having some free electrons as well. So these vacancies are also moving and these free electrons are also moving. Because of that we are getting some current. But that current was not enough because we were studying intrinsic semiconductor. Everywhere there was silicon only and number of charge carriers were also low. Like we were having electrons, we were having holes, those numbers were very low. Then we studied extrinsic semiconductor, N-type semiconductor, P-type semiconductor. In N-type, we were doping pentavalent atoms. What all are those pentavalent atoms? Phosphorus, New Zealand, Pakistan, Australia, sub BK. So you can read the name: nitrogen, phosphorus, arsenic, antimony, and bismuth. So these 5 atoms, I was doping phosphorus atom there. Phosphorus is having 5 valence shell electrons, 4 are making the bond, 1 is loosely bound. At 0 Kelvin, this particular electron is not going into the conduction band. But just as the room temperature we get, this electron is having very lesser gap between the conduction band and this donor energy level, and that gap is covered because of the thermal energy, and this electron will get excited into the conduction band. And because of the thermal energy only, some electrons from the valence band will also go to the conduction band. So there will be some holes in the valence band and there will be a lot of electrons in the conduction band. Why a lot of electrons? Because of the donor energy level. So since there are majority electrons and minority holes, both of the electrons and holes will give the current in the same direction. So total current will be added, but majority charge carriers are electrons. That's why the majority current will be because of the electrons only. Then we studied about p-type semiconductor. In p-type semiconductor, we were doping trivalent atoms. There 3 electrons were there in the outermost shell. So 3 electrons were making the bond, 1 vacancy was there. At the room temperature, no electrons could move, nothing could move, so there was no current flow. But at 300 Kelvin temperature, some electrons from the nearby atoms could fill the vacancy and create another hole. Create the same hole only. Basically, previously also you were having the hole. Now just the hole has been shifted. So now the hole can move. Along with that, because of the temperature as well, some electrons are going from the valence band to the conduction band. They are also creating some vacancy. Okay, so holes you are already having, but in the valence band, because of the boron atom, you are having a lot of holes. In the conduction band, there are minority electrons, right? So majority are the holes, minority are the electrons. Because of that, you are getting the current. Holes are drifting in the same direction of the electric field and electrons are drifting in the opposite direction to the electric field. Both are giving the current in the same direction, but majority charge carriers are holes in the p-type semiconductor. Since they are the majority charge carriers, so the current is mainly due to the holes only. So yeah, in the intrinsic semiconductor, we were having lesser current, but in the n-type and p-type semiconductor, we are having more current. And this is what we wanted. We wanted to increase the current, we wanted to increase the conductivity. Because insulator we have already made, perfect insulator we have already made. We want to go from insulator to the conductor. So that we have done. But in between, we used something called electric field intensity. So that we are going to study. Then we are going to see some classification of semiconductor. So hardly 10 to 15 minutes it will take you. Then we will study like what kind of band gap is there in insulator, what kind of band gap is there in semiconductor. In semiconductor, we have already studied the band gap. Conduction band, valence band, there is a certain gap. So like basic theory, very basic theory it is. In class 11, 12 also you would have studied it. So these kind of basic theory we will see. Then we will see that how band gap is related to the temperature. That also we will see, and then we will see that what is the meaning of doping. Like doping we have done that, but how much doping we should have done. Okay, so these things we will see. Hardly it will take 10 to 15 minutes. So I will take a break and then I will come back. I will explain these points. In the next lecture we will move. We will study about some formulas and then we will solve some questions as well. Okay then, yeah. So let me take a break and then I will come back. Yeah, hi everyone. So let's understand the meaning of these terms. So first we are going to understand about electric field intensity. Okay, so what do you mean by electric field intensity? So electric field intensity is given by negative gradient of electric potential. So we will understand that, but ignore this formula. Let's try understanding the meaning of electric field intensity. So let's just say there is this material. This material could be anything: semiconductor, conductor, insulator, it could be anything. So there is this material Across this material, what I am doing is that I am connecting a battery of V0 volt. I am assuming that here there is zero potential. If this is zero potential, that means this will also be zero potential. If this is zero, then this potential will be V0. So this potential will become V0. The 0, 0, 0, 0 will come here, and then it will make a jump to V0. So this potential will be V0, right? So this V0 potential has gone across the material. So if I call this, if I am saying that this material is having a length of L, this material is having a length of L. So if this is x equals to 0, then this will be x equals to L. Now at x equals to 0, what is the potential? V0. So I am drawing Vx versus x. What is Vx? Vx is the potential across this element, or you can say across this material. Vx is the potential across the material or element, whatever you want to call it. So at x equals to 0, what is the potential? V0. At x equals to L, what is the potential? 0. So the potential is going from V0 to 0, right? This is the graph of Vx versus x. Now if you differentiate this graph, what you will be getting? If you differentiate this graph, dVx by x, if I am calculating, what does that mean? Differentiation means simply I am calculating the slope of this graph. The slope will be minus V0 by L. This minus V0 by L multiply with negative sign. Is known as electric field. So basically your potential is decreasing in this direction, right? You started with V0 and it is decreasing to 0. Your potential is decreasing in this direction from V0 to 0. So your direction of electric field is always in the decreasing direction of the potential. Your direction of electric field. This is the direction of your electric field, right? So your direction of electric field is always in the decreasing direction of the potential. Here potential is high, here potential is low. From high to low your potential is going. So this is the direction of your electric field. That's why there is a negative sign. Are you able to understand this point? So here what will be your electric field? Your electric field would be this V0 potential is there across the length L. V0 potential is there across the length L. So your electric field is coming out to be minus V0 by L. So your electric field is V0 by L. So you don't need to care of this sign much. You will just remember E is equals to dV by dx. The sign will be taken care. How it will be taken care? You will see that how the potential is decreasing. So in the direction the potential is decreasing, that will be the direction of electric field. So you don't need to think of the sign. What you will see, across this element V0 potential has been applied and the length of this element is L. So what will be the electric field? V0 by L. What is the unit of the V0? That will be volt. And usually we will see the length will be in centimeter, millimeter or micrometer. The length will not be in meter. Okay. So electric field unit is actually unit of electric field. Unit of electric field. In SI it is volt per meter. Volt per meter. But we will usually use volt per centimeter. Why so? Because usually our length of the semiconductor will be in the centimeter or millimeter or micrometer. Are you getting this point? Okay. So volt per centimeter I can write down, volt per micrometer I can write down, volt per millimeter I can write down. Volt per meter will not be used in EDC, but SI unit is volt per meter only. Is that clear to you? All good, all fine. From here can you write down the expression of, here I should have written Vx, right? Because your potential is the function of x. Here at x equals to 0 your potential is V0, but at x equals to L your potential is 0, right? So from here can you write down the expression of Vx? Expression of Vx would be integration minus E dot dx, and here I will put the limit of x. Now this E can also be a function of x, although here it is coming constant, but it can be a function of x. Let's just say your Vx was 3 minus 2x square. This was your Vx. Then what would have been your electric field? That would be minus dVx by dx. So if you differentiate it, what you will be getting? Minus 4x, and then another minus sign is there, so you will be getting 4x. So your electric field can be a function of x as well, right? And we will see some questions where electric field will become a function of x. So it can be a function of x. So better how I should have written it. So let's remove this formula. I will write down the formula of Vx here. So Vx could be given integration minus Ex dot dx. Okay, and here I will put the limit of x. Let's just say they are asking the potential from x equals to 0 to x equals to L. So I will put x equals to 0 to x equals to L. If they are asking from x equals to 2 to x equals to 5, so x equals to 2 to x equals to 5. So this is how I can find my Vx as well. Is that clear? Very simple thing. In basics of network analysis also you would have studied it, or anywhere in EMFT as well you would have studied it. Only thing you need to remember is this. Electric field is given by minus dVx by dx. There you go. This thing you need to remember. That's it. This thing you need to remember. And from here, this thing you need to remember. Okay, so this is the meaning of electric field, and this theory I have written. The electric field intensity E at a point is defined as the rate at which electric potential Vx changes with distance. So rate of change of electric potential with respect to the distance. Rate of change of the electric potential with respect to the distance. That is your electric field. And the negative sign is indicating that electric field points in the direction of a decreasing potential. So in the direction where potential decreases, in that particular direction you get the electric field. Okay, so this is the meaning of electric field intensity. Now we will do the classifications of a semiconductor. Okay, so there are two kinds of semiconductor: elemental and compound semiconductor. Then we will see direct band gap semiconductor, indirect band gap semiconductor. So classification can be done on many things. So based on the composition, we are doing the classification here. That classification is elemental semiconductor, compound semiconductor. In ESC there can be some questions. In gate examination, questions will not be asked from this particular topic. So basically elemental semiconductor means only one element would be there, like silicon, germanium. Okay, but in compound semiconductor, two or more elements would be there: gallium arsenide, indium phosphide. So here gallium is there, arsenic is there, indium is there, phosphorus is there. So it is made of two or more elements. It is made of single element. The crystal structure is diamond. Here the crystal structure is zinc plant. When you study material science in that particular subject, which is not there in the gate syllabus, in the material science you will understand this particular crystal structure. But as of now you will just remember that silicon germanium will have a diamond type of structure, and compound semiconductor like gallium arsenide, indium phosphide will have a zinc plant semiconductor. Okay, sorry, zinc plant structure. This you will remember. This point we will discuss band gap. Here it is written, usually it is indirect. Always it will be indirect semiconductor, it is not sure. And it can be direct or indirect, anything. So as of now, you don't know what is indirect band gap semiconductor, you don't know what is direct band gap semiconductor. In the third lecture, we are going to study it. But as of now, you can just ignore this line. Just ignore this, okay? This band gap line, you can just ignore it. When we study direct band gap and indirect band gap semiconductor, at that time we will study it. Application, it will be used in making diodes, transistor and some integrated circuits. So diode we will study, transistor we will study. And it will be used in making LEDs, solar cell and laser diode. So we will study LED as well, we will study solar cell as well. So these devices also we are going to study it. Okay, so using these elemental semiconductor only you will make diodes and transistor, and using this compound semiconductor only you will make LEDs and solar cell. So these applications also we are going to study. So just a very simple point, like in a very low level of interview, they can ask you what do you mean by elemental semiconductor or compound semiconductor. So if these words are written somewhere, you should know what is the meaning. That's it. No one will ask you anything regarding this. And these indirect band gap semiconductor, direct band gap semiconductor, they are important. So we are going to study in detail. We will draw the EK diagram and we will study the meaning of direct band gap semiconductor and indirect band gap semiconductor. Also, we will study diode as well, transistor as well. All these things we are going to study. But we are not going to study the structure, diamond structure or zinc plant structure. That we are not going to study. Next, we are doing the classification of the materials. So you know there are three kinds of materials: metal, semiconductor and insulator. Now let's go in the beginning. Here we saw this energy splitting diagram, right? So we were explaining this diagram with respect to silicon, right? But if it was a metal, if your structure was a metal, then this would have been your equilibrium point. Although like I forgot to tell the name, this A naught is known as lattice constant. Okay, the name of this A naught is lattice constant. So if it was not a semiconductor, if it was a metal or if it was a conductor, then this would have been the steady state point. This would have been the equilibrium point. I should not say steady state, this would have been the equilibrium point. So here your bond would have been made. So can you see, is there any gap in the conduction band and valence band? Actually there are no conduction band, there is no valence band, there is only one band. There is only one band. Only one band is there. And there were how many electrons were there? 8 electrons were there which were available. So in the valence shell 8 electrons were available. Now these 8 electrons are having free space. Yes, they can move from here to here. In our case, in semiconductor, all these were filled, all these were empty. If this electron wants to go here, it needs to cross this energy Eg. But in this particular case, it doesn't need to cross any energy. If this electron is here, it can go here. If this electron is here, it can go here without even any energy. So they are free to move. Basically, when we studied about partially filled, this condition we studied, right? This condition we studied. So there is only one band, there is no conduction band, there is no valence band, only one band is there. In this band, some states are filled and some states are empty. Some states are filled, some states are filled, some states are empty. So if this was your equilibrium point, then you would have made a metal, or you can say then you would have made a conductor. So in conductor, there is no band gap, or you can say that conduction band and valence band overlap. Actually, there is no conduction band, valence band. But for the theory, we can say that in conductor, conduction band and valence band will be overlapping. That means there is no gap in them. That means the value of forbidden energy gap, the value of this band gap is 0 electron volt. Is that clear to you? That's why they conduct the current. So this is the thing that we have written. Yeah, so band gap 0 electron volt, copper, aluminum are the example, conductivity is very high. Okay. For the for the semiconductor, the band gap is from 0.1 to 4 electron volt. And for the insulator, the band gap will be even higher. So if you go to the insulators, if you go back to the again same diagram. So in this diagram, you can see that if I move ahead, so here the energy band gap has increased, right? So if you keep on moving here, that means if you keep on reducing the length, if you keep on reducing the distance, if you keep on reducing the interatomic distance, and let's just say your equilibrium was attained here, that means that would have made a insulator, because here the band gap is very high. Let's just say some conduction band is here, valence band is here. Now valence band electrons needs to cross this much of energy to reach to the conduction band. Valence band electrons needs to cross this much of energy to reach to the conduction band. And getting this much energy at room temperature will be very difficult. At a very high temperature only you can get this much of energy. Although at room temperature you get only 26 millivolt energy. How this much energy is enough to make the transition, that I will explain later on in some other lecture that I told you when we study Fermi direct distribution. But using that analogy as well, you will not be able to cross this much of energy because this energy is very high. So in the insulators, the band gap is very high. The forbidden energy gap is very, very high. That's why the electrons cannot make the transition from valence band to conduction band, and the total current is actually 0, right? The conductivity is pretty low. So this is what have been written there. Okay, so all 3 points you have understood. Insulators, band gap is 4 electron volt, greater than 4 electron volts. You can see the example of diamond. In diamond it is 5.5 electron volt, or in the glass as well it is even higher. So conductivity is very low, almost no conduction. So this is the classification of material based on their band gap. So only thing you need to remember is that band gap in the conductors is 0 electron volt. Valence band and conduction band are overlapping. In case of semiconductor, it is somewhere between 0.1 to 4 electron volts. For silicon, it is 1.1 electron volts. For germanium, it is 0.66 electron volt. And for insulator, it is greater than 4 electron volt. Okay. So this is what you need to remember. Now band gap versus temperature. So as the temperature increases, the band gap decreases. Okay. So let's just say I am writing down the forbidden energy gap at some temperature T is given by Eg naught minus beta naught into T. Now why that happens? So what they are saying that At higher temperatures, the atom will vibrate more. So let's go back to our this diagram again. Okay. So what we have made a silicon crystal. So silicon atoms are there. So at room temperature they are stable, but at higher temperature what will happen? They will start vibrating. They will start vibrating. They will start vibrating. At higher temperature they will also start vibrating. So if they are vibrating, then their interatomic distance will increase. Their interatomic distance will increase. And if the interatomic distance is increasing, that means you are moving towards this side. It's not that, sir, it will increase too much that you will reach here. That band gap will be completely gone. No, it will not happen. But a bit of distance will increase. Their interatomic distance will increase. And if the interatomic distance is increasing, that means in the graph you are moving here. And if you are moving towards this side, you can see that energy band gap is reducing. It will surely be semiconductor only. It's not happen that semiconductor will become conductor. No, it will not happen. Semiconductor will not become a metal. It will not become a conductor. It will be semiconductor only, but by a few amount, by a very small amount it will move. Because the distance between the interatomic distance is increasing, because atoms are vibrating. If they are vibrating, that means they are being apart. So distance will increase by a small amount. That means the energy band gap will decrease by a small amount. So it just only thing you need to remember is that with increase in temperature, the energy band gap will be reducing in the semiconductors. That's it. The relation, if you don't want to remember, then you can ignore as well. This beta naught is a constant, T is the temperature, okay, and this beta naught depends on the material, whatever the material that you are having. Also it depends on the temperature as well. Actually this formula is actually very complex. It is somewhat alpha T square beta plus 300 Kelvin. As far as I remember, this is the formula, but I don't remember the formula exactly. Okay, this is beta plus T as far as I remember. Yeah, this is the formula. Basically this formula is very complex. The only conclusion is if the temperature increases, then this value will increase. EZ naught, what is EZ naught? EZ naught is the temperature, EZ naught is the band gap at 0 Kelvin. Band gap at 0 Kelvin. Okay. So let's just try calculating the value. Let's just say at 0 Kelvin band gap is 1.18 electron volt. Now beta naught value is anything. Now I am asking what will be the band gap at 300 Kelvin. So I will put 300 here. And beta naught value will be some constant value. Okay, that will depend on the material. So what will happen? From 1.18 something will be reducing. So your answer will be 1.1 electron volt. So at the as the temperature increases, the band gap becomes lesser. Okay. So this is the thing you can keep in mind. That's it. Nothing else. You don't need to put pressure. Don't put any kind of pressure on your brain. Just remember that at higher temperature, the band gap will reduce. Okay. Because interatomic distance is increasing, and in that particular diagram, you are moving towards increasing interatomic distance. If distance is increasing, that means band gap is reducing. This formula, if you want to remember, you can remember EZ naught minus beta T. Beta is a material constant, T is the temperature in Kelvin, and EZ naught is the temperature at 0 Kelvin. Okay. Sorry, not temperature, what I am saying, band gap at 0 Kelvin. Now, in intrinsic semiconductor, what we were doing? We were doing the doping, and from there we got the extrinsic semiconductor, right? How did you get the extrinsic semiconductor? In the intrinsic semiconductor, you did the doping. Now, how much doping did you do? How much doping did you do? Based on that, there are two kinds of semiconductor: degenerate semiconductor and non-degenerate semiconductor. In your curriculum, in your syllabus, you will always study non-degenerate semiconductor only. So in the examination, if it is not given, by default you will say that my N-type semiconductor or my P-type semiconductor is non-degenerate semiconductor. So how much doping you did? Based on that, there are two kinds of semiconductor: degenerate and non-degenerate. So if you are doing very high doping, what does that mean? Let's just say in the intrinsic semiconductor, I was having 10 to the power 18 silicon atoms. 10 to the power 18 silicon atoms. 100 is 10 to the power 2. Then 1000 is 10 to the power 3. I was having 10 to the power 18 silicon atoms. Now for 10 to the power 3 silicon atoms, I am putting one phosphorus. 1 phosphorus. That means how much phosphorus I will have to put? 10 to the power 15. So in 10 to the power 18, why 10 to the power 15? Because ratio is 1 ratio 10 to the power 3. So for every 10 to the power 3 atoms, I need to put 1 phosphorus atom. If I say ratio is 1 ratio 2, and I am saying that I am having 10 rupees, that means this guy needs to have 5 rupees. How I can get this 5 value? 10 by 2. So similarly, 10 to the power 18 atoms are there, right? 10 to the power 18 atoms are there, and the ratio is 1 ratio 10 to the power 3. That means for every 10 to the power 3 atom, 1 phosphorus atom should be there. For every 10 to the power 3 silicon atom, 1 phosphorus atom should be there. That means 10 to the power 15 phosphorus atom should be there. So this is a very high doping, no? If this is the ratio 1 ratio 10 to the power 3, that means it is very high doping. And if this is the ratio 1 ratio 10 to the power 7, that means it is low doping. And since there is very high doping, that means the number of electrons will be more. And if the number of electrons are more, that means the current will also be very large. So almost metallic behavior you will get. Almost it will behave like a metal. But here you will get the semiconductor behavior. Because the doping is not very high. The doping is 1 ratio 10 to the power 7. That means this is the semiconductor. This is the semiconductor, and or I should write silicon only. I can write this is the silicon, this is the silicon, and this is the doping. Doping could be acceptor atoms, or it could be donor atom, it could be anything. So this is the silicon atom and this is the doping. So if the ratio is 1 ratio 10 to the power 3, that means it is moderately high level of doping, or you can call it degenerate semiconductor. And if the ratio is 1 ratio 10 to the power 7, that means for every 10 to the power 7 silicon atoms, you are doping 1 phosphorus atom. So total atoms were 10 to the power 18, that means you are doping 10 to the power 11 phosphorus atoms. So if you are doping 10 to the power 11 phosphorus atom, then you are good. But if you are doping 10 to the power 15 phosphorus atom, that means you are going towards degenerate semiconductor, which we are not going to study in our curriculum. In our curriculum, non-degenerate semiconductor only we study. Okay, so understood? And if doping is very high, it will give a metallic behavior. Otherwise, for moderate level of doping, it will give semiconductor behavior. Yeah, so that's it about this lecture. In this lecture, first we studied about the semiconductor. In this lecture, we haven't seen any formula. Only one formula we have seen, which is about the electric field. What all terms we have seen? We have seen drift current, right? We have seen that because of that electric field, the electron are getting some velocity. Now electrons will not move freely. There will be atoms, so there will be some hindrance. There will be some collision, so there will be some collision time. The mass of electron can also change. The mass of holes can also change. So there will be some effective mass. There will be drift velocity. There will be drift current. There will be mobility. What is mobility? Movement plus ability is mobility. That means ability to move. So all these things will be there, and we are going to understand about all these things. We are going to understand the formula of all these things in the next lecture. Okay, so I hope you enjoyed the first lecture. Here I wanted to build up the concept of semiconductor physics. That you are getting into the semiconductor physics now. You are able to understand that what we are going to study in this chapter. Formula and everything will surely come in the next lecture, and we will solve questions as well. Okay then, yeah, let's meet in the next lecture. Happy learning. Thank you very much.